To begin today's ceremony on an auspicious note, let us seek the blessings of the Almighty. I now invite Aradhana and her team to lead us in the prayer.
Palaya palaya Gauri Ganesha Parvati Nandana Gajavadana Jaya 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 He Gananatha Palaya Varada Ganesha Palaya Gauri Ganesha Jaya 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 He Lambodara Palaya Varada Ganesha Palaya Gauri Ganesha Yuga Yuga Vandita Varada Ganesha Palaya Palaya Gauri Ganesha Palaya Palaya Gauri Ganesha.
Jai Shri Ram. Good morning to one and all present here. Great beginnings truly start with great gatherings. With joy in our hearts, pride in our institution, I am deeply honored to welcome the wonderful assembly on the special occasion of our inter-school competition, 𝐅𝐴𝐻𝐾 2K25. It's our distinct privilege to welcome the president of today's function, Shri Muralidhar K, Director of Vivekananda Vidyavardhaka Sangha. And I request Srimati Vasanti K, the president of our institution, to extend a floral welcome. We are truly privileged to welcome our esteemed chief guest, Shri 𝐿𝐴𝐲 Scientific Officer, TIFR Mumbai. With great honor, I welcome you, sir. I request Srimati Shankari Sharma, the member of the management committee, to offer a floral welcome. I'd like to recognize the presence of Shri Shantanu Rai, researcher, Mangalore, and I extend a warm welcome to you, sir. I request Srimati Sindhu Viji to extend a floral welcome. I'm delighted to acknowledge the presence of Srimati Vasanti K, the president, Shri Bharat Pai, the correspondent, and Srimati Sindhu Viji, the principal of our institution. We also acknowledge the presence of Srimati Shankari Sharma, the member of management committee. A most cordial welcome to all the participants and their accompanying teachers who have gathered here today with enthusiasm, energy, and the sincere desire to excel. 𝐼𝐻𝐾 is a platform for your innovation. I extend a gracious welcome to all the esteemed judges, valued invitees, the dedicated PTA members, and parents present here today. A special welcome to the members of press and media for sharing the spirit of 𝐼𝐻𝐾 2025. A hearty welcome to our dedicated teaching and non-teaching staff and our dear students. As we come together today, let us celebrate unity, learning, and growth. Once again, a heartfelt welcome to you all. Thank you.
We now move to a significant moment of today's ceremony. I humbly request President of the function and Director of Vivekananda Vidyavardhaka Sangha to inaugurate today's function by lighting the lamp. Deepajyotihi paranjyotihi Deepajyotirjanardanaha Deepo haratu me papam Deepajyotirnamostute Shubham karotu kalyanam Arogyam sukha sambadaha Dvesha buddhi vinashaya Atmajyotirnamostute Atmajyotif pradiptaya Brahmajyotirnamostute Brahmajyotif pradiptaya Gururjyotirnamostute. Thank you, distinguished guests, for inaugurating the program.
Now, I humbly request our chief guest, Shri 𝐿𝐴𝐲 to officially inaugurate today's another event, the planetarium program, digitally. I also request Teacher Hema to kindly assist the dignitaries. you, sir, for inaugurating the program.
It's our honor to have with us Sri 𝐿 𝐸 Scientific Officer, Tata Institute of Fundamental Research, an eminent personality. I respectfully invite our chief guest to address the gathering.
Good morning. Good morning. Okay, so it's a pleasure to be here with you all on this fantastic science exhibition, and I hope I will be able to visit the planetarium myself. Let's see how it goes. I'm thankful to principal and dignitaries on the dais for inviting us to this program and giving us an opportunity to interact with you with science demos in some time. Unfortunately, I don't speak Kannada or Tulu, but my friend Shantanu speaks both the languages, so I don't think that language will be a barrier when we communicate. I'm sure you are very comfortable in English, but it's always better to converse in mother tongue. That's what I believe, and I think Vivekananda Foundation is also trying to promote our national way of education and promoting unity amongst the country. So I compliment the management committee, principal and the school for organizing such a nice program for benefit of students. And I learned that the school has started very recently, just 5-6 years ago. So within 5-6 years, I think they have done a very remarkable job, and my compliments to them for this. So thank you very much. And just one more thing. When the program begins, demo program begins, we will also tell you what Tata Institute of Fundamental Research or what science research is all about, and there probably we'll be able to talk to you at greater length and communicate the spirit of science. So thank you very much.
Thank you, sir. To share his thoughts and guidance on this occasion, I now invite Sri Muralidhar K, Director of Vivekananda Vidyavardhaka Sangha, to deliver the presidential address.
ಜೈ ಶ್ರೀರಾಮ್. ಇವತ್ತಿನ ವಿವೇಕಾನಂದ ಸೆಂಟ್ರಲ್ ಸ್ಕೂಲಿನ ಈ ವಿಶೇಷ ಕಾರ್ಯಕ್ರಮದ ವೇದಿಕೆಯಲ್ಲಿರುವ ಶಾಲಾ ಅಧ್ಯಕ್ಷರೇ ಹಾಗೂ ನಮ್ಮ ಟಾಟಾ ಇನ್ಸ್ಟಿಟ್ಯೂಟ್ ಆಫ್ ಫಂಡಮೆಂಟಲ್ ರಿಸರ್ಚಿನ ಸೈಂಟಿಸ್ಟ್ ಆಗಿರುವಂಥ ಶ್ರೀಯುತ ಉಲ್ಲಾಸ್ ವೈದ್ಯ ಅವರೇ ಹಾಗೂ ಅಲ್ಲಿಯ PG ಸ್ಟೂಡೆಂಟ್ ನಮ್ಮ ಉಡುಪಿಯವರೇ ಆದಂಥ ಶಂತಾನು ರೈ ಅವರೇ, ನಮ್ಮ CBS ಸೆಂಟ್ರಲ್ ಸ್ಕೂಲಿನ ಕರೆಸ್ಪಾಂಡೆಂಟ್ ಭರತ್ ಪೈ ಅವರೇ, ಶಾಲಾ ಮುಖ್ಯೋಪಾಧ್ಯಾಯನಾದಂಥ ಸಿಂಧು ಅವರೇ, ಶಾಲಾ ಫ್ಯಾಕಲ್ಟಿ ಟೀಮ್, ಎಲ್ಲ ಸೈನ್ಸ್ ಸ್ಪಿರಿಟ್ ತುಂಬಿರುವಂಥ ವಿದ್ಯಾರ್ಥಿ ಮಿತ್ರರೇ, ಬೇರೆ ಬೇರೆ ಶಾಲೆಯಿಂದ ಬಂದಂಥ ವಿದ್ಯಾರ್ಥಿ ಮಿತ್ರರೇ, ಪಾಲಕರೇ, ಪೋಷಕರೇ, ಮಾಧ್ಯಮದವರೇ, ಇದು ಈ ಶಾಲೆಯ ಒಂದು 3 ದಿವಸದ ಪ್ರೋಗ್ರಾಮಿನ ಮಧ್ಯದ ದಿವಸ. ಇವತ್ತು ಟಾಟಾ ಇನ್ಸ್ಟಿಟ್ಯೂಟಿನ ರೆಪ್ರೆಸೆಂಟೇಟಿವ್ ಆಗಿ ಮುಂಬೈಯಿಂದ ಶ್ರೀಯುತ ವೈದ್ಯ ಅವರು ಬಂದಿದ್ದಾರೆ. ಒಂದು ವಿಶೇಷ, ಒಂದು ಅವಿಸ್ಮರಣೀಯ ನೆನಪುಳಿಯುವಂಥ ಒಂದು ವಿಷಯ ನೆನಪಾಗ್ತಾ ಇರೋದು ಹೀಗೆ ಅಂತ ಹೇಳಿದರೆ, ಸುಮಾರು ವರ್ಷ ಹಿಂದೆ, ಸಾಧಾರಣ ಒಂದು 127 ವರ್ಷ ಹಿಂದೆ ಶ್ರೀಯುತ ಸ್ವಾಮಿ ವಿವೇಕಾನಂದ ಹಾಗೂ ಜೆಮ್ಶೆಡ್ಜಿ ಟಾಟಾ ಅವರು ಹಡಗಿನಲ್ಲಿ ಜಪಾನಿಂದ ನಾರ್ತ್ ಕೊರಿಯಾಕ್ಕೆ ಹೋಗ್ತಾ ಇದ್ರಂತೆ. ಜಪಾನಿಂದ ನಾರ್ತ್ ಕೊರಿಯಾಕ್ಕೆ ಹೋಗುವಾಗ ಒಳ್ಳೆ ಆಸಕ್ತಿ ಇರುವ ವಿಶೇಷ ಅವರ ಇರುವಂತಹ ಇಬ್ಬರು ಪರ್ಸನಾಲಿಟಿಗಳು ಮಾತಾಡುವಾಗ ಸ್ಪಿರಿಚುವಾಲಿಟಿ ಬಂತು, ಸೈನ್ಸ್ ಬಂತು. ಮಾತಾಡ್ತಾ ಉದ್ದೇಶ ದೇಶಭಕ್ತಿ ಇತ್ತಲ್ಲ, ಸೈನ್ಸ್ ಮತ್ತು ಸ್ಪಿರಿಚುವಾಲಿಟಿಯನ್ನು ಜೊತೆಗೆ ಕೊಂಡೋಗೋದು ಹೇಗೆ, ದೇಶಕ್ಕೆ ಹೇಗೆ ಹೆಲ್ಪ್ ಆಗೋದು ಅಂತ ಹೇಳುವ ಮಾತುಕತೆಯಲ್ಲಿ ಅವರಿಗೆ ತುಂಬ ಒಂದು ಫ್ರೆಂಡ್ಶಿಪ್ ಬೆಳೆಯುತ್ತಂತೆ. ಅದಾಗಿ ಸ್ವಲ್ಪ ಸಮಯ ಹಾಗೆ ಕಳೆಯಿತು. ಒಂದು 5 ವರ್ಷ ಕಳೆದ ಮೇಲೆ ಟಾಟಾ ಅವರು ವಿವೇಕಾನಂದರಿಗೆ ಪತ್ರ ಬರೆದ್ರಂತೆ, ಈ ದೇಶಕ್ಕೆ ಹೆಲ್ಪ್ ಆಗುವಂತಹ ಸೈನ್ಸ್ ಇನ್ನೋವೇಷನ್, ಇದಕ್ಕೆ ಹೆಲ್ಪ್ ಆಗುವಂತಹ ಒಂದು ವ್ಯವಸ್ಥೆಯನ್ನು ನಾವು ಮಾಡೋಣ, ಇದಕ್ಕಾಗಿ ನಿಮ್ಮ ಕೊಡುಗೆ, ನಿಮ್ಮ ಕಾಂಟ್ಯಾಕ್ಟನ್ನು ನಮಗೆ ಹೆಲ್ಪನ್ನು ಕೊಡ್ಬೋದಾ ಅಂತ. ವಿವೇಕಾನಂದರಿಗೂ ಖುಷಿಯಾಯಿತು. ಆಮೇಲೆ ಇಂಡಿಯನ್ ಇನ್ಸ್ಟಿಟ್ಯೂಟ್ ಆಫ್ ಸೈನ್ಸ್ ಈ ಥರದ ಪ್ರಾರಂಭದಿಂದ ಶುರುವಾಗಿ ನಮ್ಮ ದೇಶದಲ್ಲಿ ಆಗಲಿಕ್ಕೆ ಕಾರಣ ಆಯಿತು. 1898ರಲ್ಲಿ 5 ವರ್ಷ ನಂತರ ಈ ಕೆಲಸ ಆಯಿತು. ಈಗ ಒಂದು 127 ವರ್ಷದ ನಂತರ ಪುನಃ ವಿವೇಕಾನಂದ ಹೆಸರಿನ ಸಂಸ್ಥೆ, ಟಾಟಾ ರಿಸರ್ಚ್ ಇನ್ಸ್ಟಿಟ್ಯೂಟ್, ಈ ಎರಡು ಒಂದೇ ಸ್ಟೇಜಲ್ಲಿ ಇಲ್ಲಿ ಇರೋದು ನೋಡಲಿಕ್ಕೆ ಒಂದು ಹೆಮ್ಮೆ ಆಗ್ತದೆ. ಎಂಥ ಒಂದು ವಿಶೇಷತೆ ನೋಡಿ, ಆ ಕನ್ಸಿಸ್ಟೆನ್ಸಿ 127 132 ವರ್ಷ ಹಿಂದಿನ ಇವೆಂಟ್, ಆ ವೈಬ್ ಈಗಲೂ ಕ್ಯಾರಿ ಆನ್ ಆಗಿದೆ. ವಿವೇಕಾನಂದರ ಸ್ಪಿರಿಚುಯಾಲಿಟಿ, ಟಾಟಾ ಇನ್ಸ್ಟಿಟ್ಯೂಟಿನ ಪೇಟ್ರಿಯಾಟಿಕ್ ಸೆನ್ಸ್ ಮತ್ತು ಸೈನ್ಸಿಗೆ ಕೊಡುವಂತಹ ಒತ್ತು, ಇದೆರಡು ಕ್ಯಾರಿ ಫಾರ್ವರ್ಡ್ ಆಗ್ತಾ ಇದೆ. ಒಳ್ಳೆ ಇಂಟೆನ್ಷನ್ ಇರುವಾಗ, ಅದು ಒಳ್ಳೆ ಜನರಿಗೆ ಸಿಕ್ಕಿದಾಗ ಆ ವೈಬ್ ಜನರೇಷನಿಂದ ಕಂಟಿನ್ಯೂ ಆಗ್ತದೆ ಅಂತ ಹೇಳಲಿಕ್ಕೆ ಈ ವೇದಿಕೆಯ ಸಾಕ್ಷಿ ಅಂತ ಅನ್ನಿಸ್ತದೆ. ಟಾಟಾ ಇನ್ಸ್ಟಿಟ್ಯೂಟ್ ಆಫ್ ಫಂಡಮೆಂಟಲ್ ರಿಸರ್ಚ್ ಸ್ವಾತಂತ್ರ್ಯ ಪೂರ್ವದಲ್ಲಿ ಸ್ಟಾರ್ಟ್ ಆಯಿತು ಅಂತ ಅನ್ನಿಸ್ತದೆ. 1945 1945 ಮುಂಬೈಯಲ್ಲಿ. ಆಮೇಲೆ ಹೈದರಾಬಾದ್ ಬೇರೆ ಕಡೆಯೂ ಬ್ರಾಂಚಸ್ ಇದೆ ಅಂತ ಅನ್ನಿಸ್ತದೆ. ಫಿಸಿಕ್ಸ್, ಮ್ಯಾಥ್ಸ್, ಬಯಾಲಜಿ, ಅಟಾಮಿಕ್ ಎನರ್ಜಿ, ಇದರಲ್ಲೆಲ್ಲ ಡಿಫೆನ್ಸಿಗೆ ಸಂಬಂಧಪಟ್ಟ ಹಾಗೆ ಹಾಗೂ ಬೇರೆಲ್ಲ ಪಾಸಿಟಿವ್ ಇಂಟೆನ್ಷನ್ ಇರುವಂಥ ಆ್ಯಕ್ಟಿವಿಟಿಗೆ ಅಲ್ಲಿ ಅದೊಂದು ಯೂನಿವರ್ಸಿಟಿ, ಪಬ್ಲಿಕ್ ಡೀಮ್ಡ್ ಯೂನಿವರ್ಸಿಟಿ. ಅಲ್ಲಿಯ ಒಂದು ಲಿಂಕೇಜ್ ಮಾಡಿದಂಥ ಇಲ್ಲಿಯ ವ್ಯವಸ್ಥಾಪಕರಿಗೆ ವಿವೇಕಾನಂದ ವಿದ್ಯಾವರ್ಧಕ ಸಂಘದ ಪರವಾಗಿ ಅಭಿನಂದನೆ ಸಲ್ಲಿಸ್ತಾ ಇದ್ದೇನೆ. ಈ ಆವಿಷ್ಕಾರ ಲೋಗೋ ಇದೆಯಲ್ಲ, ಇದರಲ್ಲಿ ಒಂದು ಇನ್ನೋವೇಷನ್ ಇದೆ ನೋಡಿ, ಒಂದು ಹೊಸತನ ಇದೆ. ಅದರಲ್ಲಿ ಕೆಮಿಸ್ಟ್ರಿಯ ಟೆಸ್ಟ್ ಟ್ಯೂಬ್ ಕಾಣ್ತದೆ, ನಮ್ಮ ಸೂಕ್ಷ್ಮದರ್ಶಕ ಯಂತ್ರ ಇದೆ. 2025 ಬರೋದ್ರಲ್ಲಿ ಒಂದು ಇನ್ನೋವೇಷನ್ ಇದೆ. ಹಾಗೆ ಇನ್ನೋವೇಷನ್ ಎಲ್ಲಿಗೂ ಲಿಮಿಟ್ ಆಗೋದಿಲ್ಲ ನೋಡಿ, ಅದು ಬರೆಯುವ ಲೋಗೋ, ಕ್ರಿಯೇಟಿವಿಟಿ ಎಲ್ಲಿ ಕೂಡ ಅಪ್ಲೈ ಮಾಡ್ಬೋದು. ಸರ್ಚ್ ಮತ್ತು ರಿಸರ್ಚ್ ಇದಕ್ಕೇನು ವ್ಯತ್ಯಾಸ? ಸರ್ಚು ಹುಡುಕುವಂಥದ್ದೇ, ಹೊಸತನ್ನು ಹುಡುಕುವಂಥದ್ದು ಅಥವಾ ಕಳೆದುಕೊಂಡದನ್ನು ಹುಡುಕುವಂಥದ್ದು. ರಿಸರ್ಚ್ ಏನು, ಇನ್ನೂ ಡೀಪರ್ ಮೀನಿಂಗ್ ಅಲ್ಲ. ಇನ್ನೋವೇಷನ್ ಇದು ಸೇರಿದಾಗ ರಿಸರ್ಚ್ ಆಗ್ತದೆ. ಇನ್ನೊಂದು ವಿಷಯ ನೆನಪಾಗುವಂಥದ್ದು, 2019 ನಾವೆಲ್ಲರೂ ಸೇರಿ, ಇದೇ ಶಾಲೆಯ ಮುಖ್ಯೋಪಾಧ್ಯಾಯಿನಿ, ಅಧ್ಯಕ್ಷೆ ಅಂತ ವಸಂತಕ್ಕ, ಭರತಣ್ಣ ಹಾಗೂ ಸೈನ್ಸಲ್ಲಿ ಆಸಕ್ತಿ ಇರುವ ನಮ್ಮೆಲ್ಲರ ಫ್ಯಾಕಲ್ಟಿ ಟೀಮ್ ಸೇರಿ ನಮ್ಮ ಇನ್ನೊಂದು ಕ್ಯಾಂಪಸ್ಸಲ್ಲಿ ಅನ್ವೇಷಣಾ 2019 ಅಂತ ಮಾಡಿದ್ವಿ. ತುಂಬ ಚೆನ್ನಾಗಿ ಆಗಿತ್ತು ಆ ಇವೆಂಟ್ ಕೂಡ. ಅದೇ ವೈಬ್ ಇಲ್ಲಿ ಕ್ಯಾರಿ ಆನ್ ಆಗ್ತಾ ಇದೆ. ಈ ಥರ ಮೆಂಟಾಲಿಟಿಗೆ ಮಕ್ಕಳಿಗೆ ಏನು ಬೇಕೋ ಅಥವಾ ಮಕ್ಕಳಿಗೆ ಯಾವ ಥರದ ಕ್ವಾಲಿಟೀಸನ್ನು ಈ ಇವೆಂಟ್ ಇನ್ಕಲ್ಕೇಟ್ ಮಾಡ್ಬೋದು. ಒಂದು ಮಕ್ಕಳಲ್ಲಿ ಕ್ಯೂರಿಯಾಸಿಟಿ, ಒಂದು ಕಾಂಪಿಟೇಟಿವ್ನೆಸ್ ಇದ್ದೇ ಇದೆ. ಬೇರೆ ಬೇರೆ ಶಾಲೆಗಳಿಂದ ಬಂದಿದ್ದೀರಿ, ಪಾರ್ಟಿಸಿಪೇಷನ್ ಮಾಡಬೇಕು, ಕಾಂಪಿಟೇಷನ್ ಇರ್ತದೆ, ಆಮೇಲೆ ಸರ್ಟಿಫಿಕೇಷನ್ ಇರ್ತದೆ. ಫೋಕಸ್ ಬೇಕಲ್ಲ, ಒಳ್ಳೆ ಕೆಲಸ ಮಾಡಲಿಕ್ಕೆ, ಒಳ್ಳೆ ಇನ್ನೋವೇಷನ್ ಮಾಡಲಿಕ್ಕೆ, ಒಳ್ಳೆ ಅಚೀವ್ ಮಾಡಲಿಕ್ಕೆ, ಮತ್ತು ಇದರಲ್ಲಿ ಒಂದು ಲೆವೆಲ್ನ ಹೊಸತನವನ್ನು ವ್ಯಾಲ್ಯೂ ಆ್ಯಡ್ ಮಾಡಲಿಕ್ಕೆ ಡೀಪರ್ ಫೋಕಸ್ ಮತ್ತು ಡೆಡಿಕೇಶನ್ ಬೇಕೇ ಬೇಕು. ಇನ್ನೋವೇಷನ್ ಹೇಳುವ ವರ್ಡಲ್ಲಿ ಐಯಿಂದ ಸ್ಟಾರ್ಟ್ ಆಗ್ತದೆ. ನಾವು ಇನ್ವಾಲ್ವ್ ಆಗಬೇಕು, ಐಯನ್ ನಾನು, ನಮ್ಮಿಂದ ನಾವು ಹೆಚ್ಚು ಇನ್ವಾಲ್ವ್ ಆಗಬೇಕು, ಅವಾಗ ಇಂಪ್ಯಾಕ್ಟ್ ಆಗ್ತದೆ. ಇನ್ ನೋ ವೇ ಅಂತಲ್ಲ, ಇನ್ನು ನ್ಯೂ ವೇ ಟು ಡೂ ಅಂತ ತಿಳ್ಕೊಳ್ಬೋದೇನೋ ಇನ್ನೋವೇಷನನ್ನು. ಇನ್ನೋವೇಷನ್ ಪ್ರಾಬ್ಲಮ್ ಸಾಲ್ವ್ ಮಾಡಲಿಕ್ಕೂ ಆಗ್ತದೆ, ಅಥವಾ ಹೊಸ ಸೊಲ್ಯೂಷನನ್ನು ಫೈಂಡ್ ಔಟ್ ಮಾಡಲಿಕ್ಕೂ ಇನ್ನೋವೇಷನ್ ಅಗತ್ಯ ಇದೆ. ಇನ್ನೋವೇಷನ್ನ ಅಡ್ವಾಂಟೇಜ್ ಅಂತ, ಯಾವುದೇ ಒಂದು ವರ್ಕನ್ನು ಹೈಯರ್ ಎಫಿಷಿಯನ್ಸಿಯಲ್ಲಿ ಮಾಡ್ಬೋದು, ಅಥವಾ ಲಿವರೇಜ್ ಸಿಗ್ತದೆ. ಹೊಸ ರೀತಿಯಲ್ಲಿ ಸುಲಭಗೊಳಿಸುವ ಒಂದು ಮೆಥಡಲ್ಲಿ ಯಾವುದೇ ಒಂದು ವಿಷಯವನ್ನು ಮಾಡುವಾಗ ಸುಲಭದಲ್ಲಿ ಹೆಚ್ಚನ್ನು ಅಚೀವ್ ಮಾಡುವ ಪ್ರೊಡಕ್ಟಿವಿಟಿ ಸಿಗ್ತದೆ. ಇದರಲ್ಲಿ ಲಿವರೇಜ್ ಸಿಗ್ತದೆ. ಎಲ್ಲೆಲ್ಲ ಇನ್ನೋವೇಷನ್ ಮಾಡ್ಬೋದು, ಸಿಸ್ಟಮಲ್ಲಿ, ಎಕ್ಸಿಸ್ಟಿಂಗ್ ಸಿಸ್ಟಮಲ್ಲಿ ಇನ್ನೋವೇಷನ್ ಮಾಡ್ಬೋದು, ಮೆಥಡ್ಸಲ್ಲಿ ಮಾಡ್ಬೋದು, ಹೊಸ ಇಕ್ವಿಪ್ಮೆಂಟ್ಗಳನ್ನು ಕಂಡು ಹಿಡಿಬೋದು ಅಥವಾ ಇಂಪ್ರೊವೈಸ್ ಮಾಡ್ಬೋದು. ಬಿಸ್ನೆಸ್ ವರ್ಲ್ಡಲ್ಲಿ ಕೂಡ ಒಂದು ಹೊಸ ಎಡ್ಜ್, ಈಗ ಟಾಟಾ ಗ್ರೂಪ್ ಕೂಡ ಯಾವುದೋ ಅದು ಆಟೋಮೊಬೈಲ್ ಇರ್ಬೋದು, ಸ್ಪೇಸ್ ಇರ್ಬೋದು, ಎಗ್ರಿ ಇಕ್ವಿಪ್ಮೆಂಟ್ ಇರ್ಬೋದು, ಇನ್ನೋವೇಟಿವ್ ಪ್ರಾಡಕ್ಟ್ಗಳನ್ನು ಮಾರ್ಕೆಟಿಗೆ ತಂದಾಗ ಅವರಿಗೆ ಒಂದು ಎಡ್ಜ್ ಓವರ್ ಅದರ್ಸ್ ಸಿಗ್ತದೆ, ಅಲ್ಲಿ ಪ್ರಾಡಕ್ಟ್ ಲೀಡರ್ಶಿಪ್ ಸಿಗ್ತದೆ. ಎಲ್ಲ ಫೀಲ್ಡಲ್ಲಿ ಇನ್ನೋವೇಷನ್ ಬೇಕೇ ಬೇಕಲ್ಲ. ಈಗ ಇನ್ವೆಸ್ಟ್ಮೆಂಟ್ ಫೀಲ್ಡಲ್ಲಿ ಕೂಡ, ನಾನು ವೈಯಕ್ತಿಕವಾಗಿ ಇನ್ವೆಸ್ಟ್ಮೆಂಟ್ ಫೀಲ್ಡಲ್ಲಿ ಕೆಲಸ ಮಾಡ್ತಾ ಇರುವವ. ನಮ್ಮಲ್ಲಿ ಮ್ಯೂಚುವಲ್ ಫಂಡ್ಸ್ ಇದೆ. ಮ್ಯೂಚುವಲ್ ಫಂಡ್ಸಲ್ಲಿ ಈಗಿನ ಟ್ರೆಂಡ್ ಇನ್ನೋವೇಷನ್ ಅಪಾರ್ಚುನಿಟೀಸ್ ಫಂಡ್ ಅಂತ. ಇನ್ನೋವೇಷನ್ ಅಂದರೆ ಯಾವ ಯಾವ ಕಂಪನಿಗಳು ಹೊಸ ಹೊಸ ಇನ್ನೋವೇಷನ್ ಪ್ರಾಡಕ್ಟ್ಸ್ಗಳನ್ನು ಹೆಚ್ಚು ಇನ್ವಾಲ್ವ್ ಆಗಿ ಮಾಡ್ತಾರೆ ಅಂಥ ಕಂಪನಿಗಳನ್ನು ಆಯ್ದು ಅದರ ಶೇರಲ್ಲಿ ಇನ್ವೆಸ್ಟ್ ಮಾಡುವಂಥದ್ದು. ಅಲ್ಲಿ ಕೂಡ ಇನ್ನೋವೇಷನ್ ಇದೆ ನೋಡಿ. ಒಂದು ಫಂಡ್ ಲಾಸ್ಟ್ ಫೆಬ್ರವರಿಯಲ್ಲಿ ಸ್ಟಾರ್ಟ್ ಆದ್ದು, ಈಗ ಒಂದು 7-8 ತಿಂಗಳಲ್ಲಿ 27% ಈಲ್ಡ್ ಕೊಟ್ಟಿದೆ. ಇನ್ನೋವೇಷನ್ ಫಂಡ್ ಲೀಡ್ ಮಾಡ್ತಾ ಇದೆ. ಇನ್ನೋವೇಷನ್ ಮೈಂಡ್ಸೆಟ್, ಇನ್ನೋವೇಷನ್ ಇಂದಾಗಿ ಅಚೀವ್ಮೆಂಟ್, ಇದು ಇಂಪ್ಯಾಕ್ಟ್ ಆಗ್ತಾ ಇದೆ. ಎಲ್ಲೆಲ್ಲಿ ಇನ್ನೋವೇಷನ್ ಮಾಡ್ಬೋದು ಹೇಳಿದ್ರೆ ಎಲ್ಲಿಯೂ ಇನ್ನೋವೇಷನ್ ಮಾಡ್ಬೋದು. ನಮ್ಮ ಲೋಗೋದಲ್ಲಿ ಇನ್ನೋವೇಷನ್ ಮಾಡ್ಬೋದು, ಮಿಷಿನರೀಸ್ಗಳಲ್ಲಿ ಇನ್ನೋವೇಷನ್ ಮಾಡ್ಬೋದು, ಆರ್ಟಿಫಿಷಿಯಲ್ ಇಂಟೆಲಿಜೆನ್ಸ್, ರೋಬೋಟಿಕ್ಸ್, ಚಾಟ್ GPT ಅಂತೂ ನಿಮಗೆ ಗೊತ್ತೇ ಇದೆ. ಎಲ್ಲ ಕಡೆಗಳಲ್ಲೂ ಇನ್ನೋವೇಷನ್ಗೆ ಆಪರ್ಚುನಿಟಿ ಇದೆ. ಸಾಫ್ಟ್ವೇರ್ಸ್, ಸಿಸ್ಟಮ್ಸ್, ಎಲ್ಲ ಕಡೆ ಇನ್ನೋವೇಷನ್ ಮಾಡ್ಬೋದು. ಜನರಲಿ ನಾವು ಮಾತಾಡ್ತಾ ಇರ್ತೇವೆ, ಹೊಸ ಬಿಲ್ಡಿಂಗ್ ಆರ್ಕಿಟೆಕ್ಚರ್ ಮಾಡುವಾಗ ನ್ಯೂ ಆರ್ಕಿಟೆಕ್ಚರ್ ಡಿಸೈನ್ ಮಾಡ್ತೇವೆ. ಆವಾಗಿನ ಟ್ರೆಂಡಿಗೆ ತಕ್ಕ ಹಾಗೆ ಹೊಸ ಬಿಲ್ಡಿಂಗ್ ಕನ್ಸ್ಟ್ರಕ್ಟ್ ಮಾಡ್ತೇವೆ. ಅದೇ ಹಳತ್ತಿದ್ರೆ, ಹಳೆ ಬಿಸಿನೆಸ್ ಇದ್ದರೆ, ಹಳೆ ಬಿಲ್ಡಿಂಗ್ ಇದ್ದರೆ ರಿನೋವೇಷನ್ ಮಾಡೋದು ಅಂತ ಹೇಳ್ತೇವೆ. ಅಂದರೆ ಈಗಿನ ಟ್ರೆಂಡ್ ಮತ್ತು ಫ್ಯೂಚರ್ಗೆ ಏನು ಬೇಕು ಅದನ್ನು ನೋಡಿಕೊಂಡು ಪುನಃ ಅಪ್ಗ್ರೇಡ್ ಆಗುವಂಥದ್ದಕ್ಕೆ ರಿನೋವೇಷನ್ ಅಂತ ಹೇಳ್ಬೋದು. ಹಾಗೆ ಸರ್ಚ್, ರಿಸರ್ಚ್, ರಿನೋವೇಷನ್ ಇದೆಲ್ಲನೂ ನಮ್ಮ ಬದುಕಿನ ಒಂದು ಗ್ರೋತಿಗೆ ಹೆಲ್ಪ್ ಆಗ್ತದೆ. ಎಲ್ಲಿ ಇನ್ನೋವೇಷನ್ ಮಾಡಬೇಕು, ಎಲ್ಲಿ ಈ ಮೈಂಡ್ ಸೆಟ್ಟನ್ನು ಕಲ್ಟಿವೇಟ್ ಮಾಡುವ ಅಗತ್ಯ ಇದೆ ಅಂತ ಹೇಳಿದರೆ ಇಂತಹ ಸ್ಕೂಲ್ ಕ್ಯಾಂಪಸ್ಸಲ್ಲಿ ವಿವೇಕಾನಂದ ಸೆಂಟ್ರಲ್ ಸ್ಕೂಲ್ನ ಆಡಳಿತ ಕಮಿಟಿ ಮತ್ತು ಫ್ಯಾಕಲ್ಟಿ ಟೀಮ್ ಒಳ್ಳೆಯ ಒಂದು ಇನಿಷಿಯೇಷನ್ ತಗೊಂಡಿದೆ ಇನ್ನೋವೇಷನ್ ಮೂಲಕ. 3 ದಿವಸದ ಈ ಪ್ರೋಗ್ರಾಮ್ ಶಾಲಾ ಮಕ್ಕಳ ಕ್ಯಾಂಪಸ್ಸಲ್ಲಿ ಬೇರೆ ಶಾಲೆಯವರನ್ನು ತೊಡಗಿಸಿಕೊಂಡು ಇನ್ನೋವೇಟಿವ್ ಮೈಂಡ್ ಸೆಟ್ಟನ್ನು ಈಗಲೇ ಕಲ್ಟಿವೇಟ್ ಮಾಡಿ ಅದನ್ನು ಗ್ರೋತ್ ಮಾಡೋದರ ಮೂಲಕ ಮಕ್ಕಳಲ್ಲಿ ಮುಂದಿನ 1947ನ ನಮ್ಮ ಹೆಮ್ಮೆಯ ಪ್ರಧಾನಿ ಮೋದಿಜಿಯವರ ವಿಕಸಿತ ಭಾರತ ದೇಶಕ್ಕೆ ಸ್ವಾತಂತ್ರ್ಯ ಸಿಕ್ಕಿ 1947ನೇ ಇಸವಿಗೆ ಸಿಕ್ಕಿದ್ದು 2047ನೇ ಇಸವಿಗೆ 100 ವರ್ಷ ಆಗ್ತದೆ. ಅವಾಗ ಜಗದ್ಗುರು ಭಾರತ ಮಾಡಲಿಕ್ಕೆ, ವಿಶ್ವಗುರು ಭಾರತ ಮಾಡಲಿಕ್ಕೆ ನಾವೆಲ್ಲ ಇನ್ನೋವೇಟಿವ್ ಮೈಂಡ್ ಸೆಟ್ನವರಾಗಿರಬೇಕು. ನಮ್ಮ ಭಾರತದಲ್ಲಿ ನಾವು ಸಾಧ್ಯ ಆದಷ್ಟು ಇಂಡಿಪೆಂಡೆನ್ಸ್ ಪೊಲಿಟಿಕಲಿ ಮಾತ್ರ ಅಲ್ಲ, ಪ್ರಾಡಕ್ಟ್ಗಳಲ್ಲಿಯೂ ನಮ್ಮ ಎಲ್ಲ ಇಕ್ವಿಪ್ಮೆಂಟ್ಗಳಲ್ಲೂ ಟೆಕ್ನಾಲಜಿಗಳಲ್ಲೂ ನಾವು ಇನ್ನೋವೇಷನ್ ಮಾಡಿ ನಮ್ಮ ಇಂಡಿವಿಜುವಾಲಿಟಿಯನ್ನು ಎತ್ತಿ ಹಿಡಿದ್ರೆ ನಾವು ಇನ್ನೊಬ್ಬರನ್ನು ಡಿಪೆಂಡ್ ಆಗಲಿಕ್ಕಿಲ್ಲ. ಅಂತಹ ಭಾರತ ನಮ್ಮದಾಗಲಿ. 1947 ನಂತರ 2047ನೇ ಇಸವಿಯ 100 ವರ್ಷ ಸ್ವಾತಂತ್ರ್ಯ ಸಿಕ್ಕಿ 100 ವರ್ಷದ ಆ ಸಂಭ್ರಮ ಆಚರಿಸುವ ವೇಳೆಗೆ ನಮ್ಮ ಇಲ್ಲಿರುವ ಮಕ್ಕಳು ಇನ್ನೋವೇಟಿವ್ ಮೈಂಡ್ ಸೆಟ್ಟನ್ನು ಕಲ್ಟಿವೇಟ್ ಮಾಡಿ ಇನ್ನೋವೇಷನನ್ನೇ ಒಂದು ಉಸಿರಾಗಿ ತಕ್ಕೊಂಡು ಹೊಸ ವಿಚಾರಗಳನ್ನು ಎಲ್ಲ ಫೀಲ್ಡಲ್ಲಿಯೂ ಅವರವರ ಉದ್ಯೋಗ ಕ್ಷೇತ್ರದಲ್ಲೂ ಮಾಡಿಕೊಂಡು ಈ ಭಾರತಕ್ಕೆ ಕೊಡುಗೆ ನೀಡಿ ಭಾರತದ ಕೀರ್ತಿಯನ್ನು ಇನ್ನಷ್ಟು ಎತ್ತರಕ್ಕೆ ಏರಿಸಿ ನಮ್ಮ ಈ ವಿವೇಕಾನಂದ ವಿದ್ಯಾಸಂಸ್ಥೆಗಳಿಗೂ ಟಾಟಾದಂತಹ ಆ ಒಂದು ವಿಶೇಷ ಪೇಟ್ರಿಯಾಟಿಕ್ ಸೆನ್ಸ್ ಇರುವ ಸಂಸ್ಥೆಗಳಂಥವರಿಗೂ ಒಂದು ಹೆಮ್ಮೆ ತರುವಂಥ ಕೆಲಸ ಮಾಡಲಿ. ವಿವೇಕಾನಂದ ಸೆಂಟ್ರಲ್ ಸ್ಕೂಲಿನ ಈ ಒಂದು ಪ್ರಯತ್ನ ಯಶಸ್ವಿಯಾಗಲಿ, ಇದು ಕನ್ಸಿಸ್ಟೆಂಟ್ ಆಗಿ ಮುಂದುವರಿಲಿ ಅಂತ ಆಶಿಸ್ತಾ ಎಲ್ಲರಿಗೂ ಶುಭಾಶಯಗಳನ್ನು ಹೇಳ್ತೇನೆ. ವಂದನೆಗಳು.
Thank you, sir, for your encouraging and visionary message. Now, I request President Shri Muralidhara K to present the memento as a token of gratitude to Shri 𝐿 𝐶𝐻.
I request to give the memento to Shantanu sir also. To conclude the ceremony, I invite teacher Veena to propose the vote of thanks and express our gratitude to all who made this event possible.
Jai Shri Ram. Education and science together illuminate the path towards a brighter tomorrow. Good morning to all present here, dignitaries on the dais and off the dais. It is my great honor to deliver the vote of thanks on this special occasion, Avishkar 2K25. First of all, I am sincerely grateful to Shri Muralidhara K, Director of Vivekananda Vidyavardhaka Sangha, for presiding over today's function. Your support inspires us to promote science in education. We are deeply honored to have our chief guest, Shri 𝐿 Scientific Officer, TIFR Mumbai, with us today. And we are sure that TIFR outreach session, the wonderful lab called Home, will inspire our students to explore, innovate, and continue questioning the world around them. Thank you, sir. I express my sincere gratitude to Shri Shantanu Rai, researcher, Mangalore, who is all set to support and encourage our curious minds. Thank you, sir. I sincerely acknowledge the gracious presence of Srimati Vasanthi K, President, Shri Bharat Pai, Correspondent of the School Governing Council, Principal Srimati Ms. Sindhu VG, whose dedication and guidance always inspire us. Committee. I express my sincere gratitude to all the judges, to the members of the School Governing Council, teaching and non-teaching staff, and all our students for their unwavering support. We extend our heartfelt gratitude to the press and media for recording and sharing the highlights of today's event. To all the invitees, PTA members, parents, and well-wishers for their unwavering support. Your presence has added great value to the special day. My best wishes to all the participants.
With this, we formally conclude today's program. Thank you all for your gracious presence. Have a wonderful day.
We request all the competitors to full entrance near the registration desk as the competitions will begin shortly in the respective rooms. Students holding name placards will guide the...
Okay, namaskara. So, it actually everything begins with a play. Science begins with play. How many of you like to play? Oh, everyone. That's great. So, it begins with very everyday objects. So, Shantanu, you went to school very recently, right? You were a school kid till very recently.
Yes.
So, what all did you used to carry in your bag?
I used to carry, like in my pencil box, I used to have a pencil.
Okay.
I used to have an eraser. I used
Okay.
to have rubber bands.
Okay. What
Or
else?
Water bottle I used to carry in my bag.
Yes, and
And in school, we used to play chalk sometimes.
so did your teachers used to throw chalks at you for not obeying them?
No.
See, they are happy. I think their teachers do throw chalks at them. So it's good. So chalks. So our first experiment, let's begin with a chalk and activity of throwing or dropping the chalk.
Okay.
And do you guys think there could be some science in this? Or no, it's just something. So what do you guys think? Like he says that, or I say that with the help of chalk and throwing the dropping of chalks, we can show a basic science experiment.
But what can we show?
Let's see.
Okay.
Let's see. So all I want to do is, okay, I give you a chalk. Okay. You have to break it such that one piece is much larger than others.
Okay.
Hold it between your fingers, both the pieces like this, and drop. And you guys have to say which piece will touch the floor first. The bigger one, heavier one, or the smaller one. That's the thing. Okay? So, just let's make a guess. Why don't you come forward? So, I break this chalk. Okay? Now, obviously, one is much larger than another, okay? And he is to hold the chalks in his pinch like this, such that the lower levels are at the same height, and drop them on your count. So you count 1, 2, 3, he will open his fingers and the chalks should drop. Is that correct? So now, which chalk, will the heavier chalk drop first or will the lighter one drop first? So, heavier. Okay, so how many people say heavier chalk will drop first? Quite a lot of people. And how many think that the lighter piece will fall first? Okay, and who are with our young friend? He says both the chalks will fall at the same time, right? Anyway, you also think both the chalks should fall? No, you don't think so. You think so. All right, so this is how the science actually begins. The science is all about making a hypothesis, designing an experiment to test the hypothesis, performing the experiment, and trying to understand the experiment. So it cannot be that I claim that something is true and I expect people to accept it as truth without a scientific test of experiment. Okay? So science is all about verification, re-verification, and doing the verification in different ways just to make sure that what was perceived as truth is indeed the truth. So is it time to do the experiment?
Yes, let's do it.
So hold the chalks and you have to give him a count. 1, 2, 3. Okay, I'm not going to give him a count. Wait. Are you holding them at the same level? No cheating. Okay? All right? So guys, ready? Give him a count. 1, 2, 3. And which one? Both. But then many of us had said that heavier chalk will fall first. What happened to that? Or shall we redo it? Let's do it one more time.
Yes.
Okay. Let's do it one more time.
I'll try to do it from a higher height.
Okay. Yeah, or maybe you can drop them to the floor. Then okay. So raise your hand. Yeah. Yeah? Yeah? Give him a count one more time. Both. Okay. So, all right. So what he did just now is this some famous experiment?
Yeah, I think Galileo did the same experiment.
Yeah, you guys have heard the name Galileo, of course, right? Galileo Galilei. Okay. So Galileo Galilei, who was a mathematician in around 14th century in Europe, Italy to be very precise, and he is considered as a father of modern science, because modern science is all about what I just mentioned to you in the first thing. Like, you hypothesize, you kind of consider a situation, consider a possible outcome, design an experiment, perform the experiment, and what happens in that experiment, you accept it as a truth. Okay? Because I can hypothesize anything. Like, I say that this man is 1,000 kgs. Is it true?
No.
Okay. He says that I am only 10 kgs. But the test will be an experiment. If we make him stand on a weighing scale, if he weighs 1,000 kgs, we accept it. If I weigh 10 kgs, we accept it. But otherwise, whatever is shown, we accept it. That's the point. So, would you guys like to do this experiment at home? When you get home, see, what we are trying to show you today is, for explorations and for thinking up scientifically, one doesn't require any high-level laboratories or expensive equipment or anything of that kind. The first requirement is curiosity. Curiosity is just ability to think differently, be curious about why the things are the way they are, and what will happen if I do certain thing or if I don't do certain thing. Hey, can you guys see what he's doing, or there's a problem? People there? You are able to see it. So, during this entire session, all that we'll try to impress upon you and try to convince you is two things. Firstly, curiosity. Curiosity is utmost important in science or in general in life, because that will give you a purpose for work. And second is ability to think independently. That's a very important thing. And no matter what the world says, you have to be true to your convictions, your experimental methodologies, and what the experiments show. Like, there is a very famous story of Einstein that you might have heard, that when he wrote his theory of relativity, the predictions of that theory were initially thought to be very strange, and many people started saying that no, all this is wrong. Okay? And then that time a lot of scientists started writing letters as to why and how the theory is incorrect, inconsistent, and inadequate, etc., etc. To that, Einstein gave a very epic response. And the response was, if I am wrong, I don't need 100 people to tell me that I am wrong. Only one is sufficient, but he has to prove it. Okay? Mere saying is not sufficient. That proof has to be there. Okay? So this is about a simple experiment which Galileo did. And now let's move on. And what will be the next experiment you want to try? Say, what do you have? You have paper? Okay. So, what is gravity? Have you heard? You must have heard the term gravity, right? What is gravity?
He wants to answer.
Aha. You want to answer? Yeah. Come forward. We can run a mic.
The force that attracts object towards Earth is called gravity.
Okay. So, did the chalk fall down because of gravity? Did the chalk fall down in his earlier experiment? Did it fall down because of gravity? Did it? Or was it something else?
It was gravity.
Gravity. Okay. So, gravity is the free fall acceleration. Now, is it possible that something can fall faster than g? Can we imagine a scene? See, right now we are just trying to do experiments which involve dropping the things, throwing the things, and perhaps breaking the things. How many of you guys like to break your toys? Ah, okay, good, good. And do you get bashing for it? Okay, all right. So now the test is very simple. That he's going to hold the chalk. Okay, you can perhaps hold in both the hands, and maybe one of you can come. Can one of you come? Anyone, please come. Please come. Yeah, we'll call. Please come. Okay, you know what to do. Do you know what to do? Not throw the chalk. So not throw the chalk. Just hold it. Stretch your arm. No. Hold it on your palm. Okay? And just repeat what he does. Okay? Now, guys, observe very carefully what he does. Okay? Yeah. Yeah. So what fell fast? Did your hand fall faster than the chalk? Did your hand come down faster than the chalk? Was there a gap? There was a gap. So why was the gap there? See, let's redo it. You can be at your seats and do it. You have some pen or something? Anything in your bag? Any small thing, any coin that you have, you can do it. So just hold it flat, hold it horizontal. Okay? And just drag your hand down. Don't throw your watch, it will break. I mean, if it breaks, I can't replace it. Okay? So, what is the outcome of this tiny experiment? What is the outcome of this tiny experiment? Okay, don't worry, we'll tell you. So, Shantanu, what did we conclude?
Like when I moved my hand like this, there was a gap between the chalk and my hand.
Did everybody see the gap? Yes. Okay. So, what does that gap mean?
So I think I moved my hands faster than gravity.
Okay. So, what you are trying to tell everybody is, gravity is not the upper limit. You can accelerate things at a rate faster than the gravity. Okay. Okay. Thank you very much. This is our one tiny experiment. See, the purpose of demonstrating this experiment is just think differently. You have what you have and try to explore what can be done using what you have. So let's go ahead and start with our more experiment of dropping the things. Now, I take a piece of paper, and do you have a notebook? Yeah. Here we have a notebook. So, now I'm going to demonstrate in front of you an experiment. Right now we hypothesize that whether the thing is heavy or light, they fall at the same time, right? Experiment is same. Now the objects are different. On one hand, I have a notebook, and in my another hand, I have a piece of paper. So which one is heavier? Paper? Book. Okay, book is heavier. So now if I drop the things at the same time, will they touch the floor at the same time? But earlier experiment you saw everything different. You said things should touch at the same time. Confused? Let's do an experiment to start with. Okay? So you take this and take this, and again, will you give him a count or shall I give him a count? Okay, all right. So hold it flat, both the things, yeah? And no, you can hold it in the pinch. Paper, you can hold it in the pinch. Yeah. All right. So please go ahead and help him perform the experiment. And the heavier object fell down faster. So, do we see a contradiction with our earlier experiment? We see, right? How many people see a contradiction? Okay. Everybody sees a contradiction. So now we have to think, earlier we hypothesized that things should fall independent of their weight, independent of their mass. But in the second experiment, we are seeing something different. Anybody in 10th class? 9th or 10th class? Okay. So you guys must have done this experiment in the class, right? So what is the explanation? Anybody? Shall we run the mic? Shall we run the mic in the audience? Yeah. Anybody? What is the explanation? Or do you think we did something wrong? Is everybody convinced with the experiment? or not convinced with the experiment? Say yes or no. It's okay to say no. Everybody is convinced with the experiment. Yes. Yes. So why did the paper take much longer to fall down over the notebook? What is the explanation? Air resistance. That's correct. So now, if he has to overcome the air resistance, who said air resistance? Yeah, okay, good. So why don't you come on stage? Please come. We need your help. Yeah, come. So give him a big hand. He gave the right answer, air resistance. Okay. So now he wants to make sure that both the things fall at the same time. Help him. He wants to make sure that both things should fall at the same time. Help him. How?
So I want to put both at the same time. Same time ಬೀಳ್ಬೇಕು ಎರಡು ಕೂಡ.
But you won't get it, no? Yeah, but now the thing is, you are right. So because of air resistance, this paper took longer. It is bigger, okay, also lighter. So air resistance took longer. Now we have a very simple objective. We want both the things to fall at the same time. How will you do it?
If we keep this book on top of the paper, the book will push the paper. So
the air resistance will not matter. Okay. So do you want to confirm it?
Yes.
Okay. Go ahead. Yeah. All right. Great. So the point is, what's your name? Oh, okay. What Gautam showed just now is a very little experiment, but it is very important in scientific temper. That he thought a way of doing it, that a way he can make both the things fall at the same time is by way of putting one top of another. Right? So that's only a hypothesis. Unless he does it and verifies that it indeed happens that way, can the hypothesis be said to be true? No. Let me say it again. See, he made a hypothesis that if he keeps the things like this or even like this, okay, things will fall at the same time. But this is only a thinking, a hypothesis, right? So unless he does it, will you believe it? Will you believe something just because Gautam said it will be that way? No, right? So you will demand an experimental proof. So he did the experiment and he has said it right. So thank you very much. Good job. Which class are you? Fifth class. Same school or some other school? Same school. Okay, good, great. Please sit.
But Ullas, what if we do it the other way around? Will it still work?
Right?
So what do you think? Will both of them fall at the same time or different time? Different time.
Okay, give me the mic. 1, 2, 3. Okay, because you allowed the air to come in between. Yes. Okay? Now, if suppose you fold the paper, make sure that, it is of the same size. Yeah. Now you drop it, but you will see the same result because there is air in between your sheets. Okay? All right. So let's move on. And now from dropping the things, let's do some simple experiment. Okay. So the thing is, now what we want Shantanu is, we want him to walk from one edge of the stage to other edge of the stage. And you have to just say what was his speed. Was it constant or was it changing? Okay, will you do that?
Okay.
Okay, so let me make some space for you. All right, so, yeah, okay. So, yeah, all right. All right. So, was it at the same speed? Yes. Okay, now let us say that his speed is some x meters per second. Now, would you walk a bit faster? Okay. Now, is it still the same? No. So, it is higher than that. Okay. So, if you have to draw this, do we have a picture of this? Yeah. Okay. So, let us just show you a slide and then connect it with the next experiment. Okay, so in this graph, what is shown is speed as a function of time. So since he walked at the same speed, it is a flat horizontal line. Then can we go to the next? Since he walked faster, we see that the speed is high. Now let's go to the next part, and now this will be a question to you, that we are going to walk on the stage. He is going to walk at a different speed. I am going to walk at some different speed. And once you please observe carefully, and then we will ask you a question. So we'll start from here. Yeah, because I walk a bit slower. I start first. I walk a bit slower. You go faster. Okay? I'm an old man, right? I like to walk at leisure. Okay? Okay, all right. So whose speed was higher? His speed was higher. Okay, now comes the question. When he crossed me, what was our speed? Were we at the same speed or were we at a different speed? How? Different speed. All of you think it was at a different speed? Or is there somebody who thinks that at the instance when we crossed? At the instance. See, look at this graph. So let us say that he started walking from here, we started walking from here. I was initially here and then he came from behind and he crossed me. So the instance when he crossed me, at that point, at that instance, were we at the same speed or were we at a different speed? We were at the same speed. Okay? How many people think that at the instance he crossed me, our speeds were exactly the same? Okay, quite a few people think that our speeds were exactly the same. How many people think that I was faster than him? Nobody. And how many think that he was faster than me? Okay? So the ones who think he was faster than me, can somebody explain how? Because, yeah, but see, again, I'm asking you a very simple question. We are asking about a simple point. At that point, when we were actually parallel to each other, what was our speed? Were we at the same speed or were we at the different speed? That is the question. So you want to say it in Kannada? Huh. Yeah. So let him say this question in Kannada just for the benefit of clarity.
So ನಾವು ಕ್ರಾಸ್ ಮಾಡುವಾಗ ಯಾವ ಸ್ಪೀಡಲ್ಲಿ ಇದ್ವಿ? ವೇರ್ ವಿ ನಮ್ಮ ಸ್ಪೀಡ್ ಸೇಮ್ ಇತ್ತಾ ಡಿಫ್ರೆಂಟ್ ಇತ್ತಾ ಅಂತ ಕ್ವಶನ್ ಕೇಳ್ತಿದ್ದಾರೆ. ಸೊ ಡಿಫ್ರೆಂಟ್ ಯಾರೆಲ್ಲ ಹೇಳ್ತಿದ್ದೀರಿ? ಯಾರಾದರೂ ಎಕ್ಸ್ಪ್ಲೇನ್ ಮಾಡ್ಬೋದು ಯಾಕೆ ಅಂತ?
Yeah, okay, all right. So you guys are correct because intuitively it is correct. But the thing is, many people think that at the time of crossing, our speeds were same. There are few people, right? Yeah, so it's not so. See, his speed was, he was walking independent of me, I was walking independent of him. So there is no reason why his speed would be same as my speed or other way around. Okay, so this is so much about walking, and now let's go over to the next experiment. No, okay. So you have a ballpoint pen?
Yes.
Okay,
Yes.
so can we, all right, so everybody has a ballpoint pen? Okay, so please take out your pen. And this is a simple experiment about pressure. So just keep it in your palm and hold the other hand like this. Everybody, are you able to do it? So where do you feel the pressure? Down. Okay, now just flip it. Now where do you feel the pressure? No, you are not doing the experiment. You do the experiment and tell me. So let's do it one more time. Take a pen or pencil. Let one end be sharp and one end be blunt. And just keep the sharp end in one palm and press the other palm on the other side. Okay? All right. So in this position, my left hand, which is lower hand right now, I'm going to feel a much higher pressure. Is that correct? Are you guys experiencing the same thing? Okay. Now just turn your hands around. Okay. Now do you see it reversed? Or is it still the same, that the hand with a sharper tip is feeling more pressure? Okay. So now, why is it like this? We did an experiment, simple experiment. We are trying to feel the pressure. Okay. So anybody? Yeah, go ahead, go ahead. You raised your hand, right? Yeah, go ahead. Yeah. So pressure is force upon unit area, right? So that's the simple experiment. You experience the pressure, and you also see that pressure is a function of area. You must have seen this. You must have seen this formula in the textbook, right? But this is a very easy way to connect what is there in the book with your everyday experience. Otherwise, how do you know what is written in the book is correct? All this time, we are trying to impress upon you the same thing, the experimental validation of what is presented to you. Anything. It could be in the book, it could be in the real life. Is that correct?
Yeah.
Okay. So, all right. Now, where do we go next from here? We have played with ballpoint pen, and so let's look at the. Do you have a ruler?
We have a ruler.
We have a ruler. Okay. Now, is this a standard ruler or some special ruler?
Standard 30 centimeter ruler.
Okay. Let's see. Let's see. Do you guys have a ruler with you? No? Okay. You can do this experiment with pen as well. Now, what Shantanu will do is, he's going to hold the ruler on his both the fingers. Okay. Roll it. Hold it straight. Hold it straight. Yeah. Okay. And he is going to bring his hands closer. Have you seen this experiment before? Okay. So you can tell us what this experiment is all about and what will happen. Who said who has seen this experiment? Yeah, go ahead. Come on. No, it's okay. Come on. Come on. Come on. Come on. Help him do the experiment. Come. It's okay. Yeah. So you are going to tell him what to do. Shall I give you the mic? Okay then. Go ahead. Okay. And
to the midpoint.
to the midpoint. But will he see? He's going to move his only one hand. He's not going to move both the hands. Okay. I can hold his hand and make sure that he doesn't move the other hand.
Okay.
This hand. Okay. And now let's see what happens. Okay. Go ahead. So, what did you see?
That the midpoint holds more pressure.
No, there is no pressure thing here. No?
I mean.
Okay, let's do it one more time.
Should I close my eyes and do it?
Yeah, you should close your eyes, correct?
There's a blindfold.
Shall we put a blindfold? Shall we close his eyes with a...
Sure.
Okay. All right, so no cheating. All right. Hold it. Yeah. Shall he start? Hold your elbows straight. Yeah. Okay. Go ahead. Start. Hold it horizontal. Yeah. All right. Now your hands have met. Let us see where they have met. They have met at about 15 centimeters, which is this halfway?
Yeah.
Okay. So now, why did it happen this way? He was moving only one hand. Okay. But practically, when his hands met, he was at the center. Why was it like this? That's the question. You don't know? Just make a guess. It's okay to make a guess.
I have no guesses.
Okay, all right. So that's also correct, because it's better to say I don't know rather than giving something a wild guess answer. So that's correct. In fact, it's very important that if somebody says he or she doesn't know, and he or she admits he or she doesn't know, it's actually a good thing, because a listener will normally believe what you say. And if you honestly say you don't know, then the person knows that you are honest. So that's good. So keep it up. Okay, thank you. Now, coming to the experiment, this was a demonstration of what is called as center of mass. Now, center of mass is a very funny thing. Do you guys think that our human bodies also have a center of mass? Where is it? I mean, is it in my shoulders, or is it at my knees, or is it at my waist? Where is it, roughly? Everybody has a center of mass. Where is it? It's at the waist. How many people think that it's at the shoulders? Nobody? How many people think that it's at the knees? So let's repeat the question. We are saying that this scale has a mass, okay? And we can consider at a much larger, when we consider relatively, we can say that there is something called as a center of mass for this object, which is roughly we say that whether we go in this side or this side, we'll find the same mass. So that is the center of mass. So now we say that human body also has a center of mass. Okay. Now, what happens if the center of mass shifts? Let us say what happens with the center of mass shifts.
Okay.
So how do we shift the center of mass? We say that this is uniform, right? If we have to shift the center of mass, what is it that we'll have to do? What can we do? Either we start cutting it from one side, but then the center of mass will shift, right? So now let's add some weight to this side. Let us say that we add a coin and tie it with a rubber band. Okay. Okay. Let's take a coin. Let's take 2 coins. Okay. And do you think the coins will go away, fly away? Or they will stay?
No, they will stay.
All right. So now what we have done is we have increased the mass slightly on one side and created an imbalance. So now when he does the same experiment again, do you think that his hands will meet at 15 centimeters? No, right? Which side it will shift? Will it shift to my right, that is the lighter side, or will it shift to the heavier side? Heavier side. Okay, because we see that the density is now changed and heavier thing is on this side, so the center of mass will come on this side. So this is our little demonstration of center of mass. Now, why do we discuss this center of mass? So, does Earth revolve around the sun? Yes. And if he is the Earth and I am the sun, can I say that we are actually revolving around each other about our center of mass? No? Well, actually it is true. But the thing is that sun is much, much bigger than Earth. And it so happens that this so-called center of mass of Earth and sun is between the sun. It's within the sun. Okay? So it's not somewhere in between, but it's within the sun, and it is this center of mass about which the Earth actually rotates. Is that the thing we have an elliptical orbit?
Oh, is that why we have elliptical orbits? I am also not sure.
What do you guys think? Is the Earth path around sun, is it elliptical or is it circular? Yeah, so the question is, why is it elliptical? So think about it. Think about it. Since you are going to see the planetarium, you can ask this question in the planetarium as well. And also confirm whether it is really the way I said it is. Okay, because it's also important that I don't want you to believe what I say because I say it. You please think independently, test it, and depending on the result of the test, you can accept it or reject it. Okay, so now let's go next and let's play with water. Okay, so let's do a very simple experiment. Again, we need to put some color. Okay, let's take a cup of water. Yeah, can you, no, we have this food color. We'll put some food color in this. So I'm going to do an experiment. In this, normally we see that things fall, right? If I leave them, things fall. But in this experiment, we'll see this test tube actually going other way up. Okay? So for that, let us say that, shall we take this table a bit forward? So I take some water in this test tube and I have colored it just so that everybody can see it. Okay. Do you see this? Okay. Now, if I put this test tube in it, which is empty, there is nothing in this. Okay. And if I reverse this, what will happen? Okay.
Our test tube in reverse agi hakidre ಏನು ಆಗ್ತದೆ?
So do you expect this test tube to fall down? No. Okay, let's do this. Let's see. Is anything happening? Okay, let's hold it. And just to accelerate it, let's reduce the water a bit. So do you see that it is falling against the gravity? Did it go in? Okay, let's do it one more time, because I think it was not very visible. Okay, let's reduce the water somewhat. Do you see it moving up? Is it moving against the gravity? Is it or is it not? So I have taken some water, about 50% of the tube. I have put in another small tube that snugly gets in. Okay, removed all the air in between and simply reverse this. Do you see the smaller tube is moving against the gravity and going up?
Very, very slowly.
Yeah, it is going to be slow. That's another observation. Do you see the rate of movement changing? Is it accelerated? Okay. So, is everybody convinced with the experiment? Or do you want to do it again? Do it again. Okay. All right. So to start with, I have two test tubes. One is slightly bigger and other one is slightly smaller than this. Not very small. It just snugly gets in. Okay. Something like this. And I'm taking about 50% of this test tube filled with colored water. Color is only for visibility, that's all. And then I'm putting this other test tube in it and removing all the air. Okay, so I have removed all the air and I'm flipping it. See, I'm not pushing this tube, I'm only leaving it. And now let's see what happens. Do you still see water coming out? Okay, and is the smaller tube going up?
It's going up very, very slowly.
Is it going slowly or is it going at some uniform speed or is it getting faster? Yeah, it is slow, but is it getting relatively fast? Okay?
It seems like it's going a bit faster.
Yeah, so it is accelerating, right? So if speed is constantly increasing, then we'll call it accelerating. If it is constantly reducing, then we'll call it decelerating. And now it has hit the limit. Okay, so now the question is, why did we see this tube actually moved against the gravity? It moved against the gravity, right? Because of gravity, we would have otherwise expected it to fall down. But in this experiment, when I was holding it like this, see, now it will not move. Is it moving now? Okay, but with water it moved up. So the question is why? So we performed this tiny experiment, and now idea is to know why did it happen this way. So many of you can probably do this experiment at home. You may not have glass test tubes, but you could have something which is almost of the same size. You can do it in a steel cup or anything. So anybody who can give an answer? It's okay to make a guess. To start with, we can make a guess and then we can test the guess with some other experiment. But air pressure where?
When the water fell down from the bigger tube, to cover the air, the smaller tube went up.
To cover the gap.
Yes.
So that's correct, because air is all around us, and when the water started dripping, there was a lower pressure created in the upper tube, and that because of that the ambient pressure pushed the tube inside. That's correct. So can I give you the small reward of these test tubes? This is a small reward to you. Play with them. Just don't cut yourself. Don't break the glass and cut yourself. Okay? All right. So let's move on. So guys, would you like to look at some puzzle? Shall we give you a puzzle to think about and we'll take a small break? Huh? Does it work?
Okay.
Sir, is it okay? Okay. So our Shantanu, okay, he is a computer scientist. Computer scientists program nahi likhte hai. Is that correct? This is not the main job.
I mean, computer scientists in general, right? But we at TIFR are more theoretical people. So we study theoretical problems in computer science.
Okay. So what exactly do you do? What do you mean by theoretical problem in computer science?
So we try to make things more efficient. So if there is any task we want to do, the task ಮಾಡ್ಲಿಕ್ಕಿದ್ರೆ, we try to find out how to do it fast in less time or using less space, something like that.
So basically what he is trying to do, or what people in his area do, is given a task can be very complex, because in modern science there is nothing that can be actually called as simple, right? And there is always a need to do anything or everything in a more efficient, time efficient and resource efficient way. And you guys try to devise the methods for that.
Yes.
Is that correct?
Yes.
Okay. So how many of you would actually like to become a scientist later on?
Oh.
Okay, that's a good number. It's a good number. So since you want to become a scientist, let me just give you a few tidbits about what scientists actually do. So scientists, the first is they wonder. They wonder about nature. They wonder about things in nature, and they wonder about why the things are the way they are, and why can't the things be in a certain way. And they work towards finding ways to do that, either to prove it or disprove it. So the modern scientific research happens in several areas, several different areas, certainly broad areas like physics, chemistry, mathematics, biology, computer science. But there are also sciences which are interconnected. So nature is one, science is one, and things are interdependent and connected. So there are people who do biological physics, chemical biology, mathematical biology, and things like that, which when you grow up, if you take up science stream, you will come across. But the most important thing in science is explorations, the desire to keep exploring. That's what makes a scientist. Because many of the questions are right now very trivial, because just imagine the times of Galileo when he did this famous experiment that we repeated as the first experiment today. People, by and large, they might have had seen what he saw, but they never really tried to scientifically formulate it. So what is important is the scientific attitude and scientific temperament. And no matter what the world thinks, what the world says, you go about your task. Because many of the things that a scientist does, rest of the world may think it to be a bit irrelevant. Okay, so with this, let's take a puzzle. Yeah. And what do we have?
So we will try to do a puzzle, a task that seems impossible at first. Okay, so I'll need 2 volunteers. So
yeah, one guy and one girl perhaps?
Yes.
Okay, one guy and one girl.
Come on.
But you don't know what the puzzle is. What if he asks you to jump, make 100 jumps? Will you do it? He'll do it. Do you know the puzzle? But if he asks you also to make 100 jumps, will you do it? She will do it. Okay, all right. So they are ready for the puzzle.
ನಿಮ್ಮ ಹೆಸರೇನು? ಸನ್ಮಿತ್. ಅಭಿಜ್ಞ.
Okay, so please come in front. Please come in front. We'll just take out the table. So what you do should be visible to everybody. It's okay. It's a very simple puzzle. Very fun stuff.
Okay.
Okay.
ಇದೊಂದು ಸಿಂಪಲ್ ಪಜಲ್. ಸೊ ಅಭಿಜ್ಞ. ಸನ್ಮಿತ್.
Sanmit and Abhignya. So is he the jeweler?
No, she is the jeweler.
She is the jeweler. Okay, all right.
Okay.
So you have a jewelry shop. Let's assume you have a jewelry shop. You are a jeweler and you go to him to buy some gold and silver. You go to her shop. Okay. Okay. Now she has silver and gold. Okay. Now let's see. So which is silver? So which one is silver? In her left hand or right hand? No, no. In her left or right? Silver is left and right is gold. And does she have one more silver?
She has.
Yeah. And it so happens that she has 2 bars of silver. So Sanmit wants to buy gold and silver bar. A rich man. Good. Okay. And she is the seller. But now here is the twist that unfortunately Sanmit can't see anything. He is visually impaired. Only for the puzzle. Okay. So we'll cover your eyes. And it so happens that okay, are you able to see?
You're able to see?
No, you're not able to see.
How much is this? Can see? No.
No. Okay. All right. So now you please ask her. What are you going to ask her?
Can I get a bar of silver and gold?
Okay. So what will you say? Do you want to sell him or you don't want to sell him?
Okay, I'll sell.
You are willing to sell, or you are going to say no, nothing
I'll
for you.
sell.
Go away.
I'll sell.
Okay, you will sell. Okay. So please go ahead. I can hold the mic for you. Okay.
Here you go. Thank you.
Okay. So hold it in. Okay. Yeah. This is. So she has given you 2 bars.
Yes.
Okay. Now.
What did you give in his right hand?
A silver. Gold.
Okay. Now see. Let's put it this way. She is claiming that she has given 1 gold and 1 silver bar to Sanmit. Okay. And unfortunately, since he can't see, he is going to believe it. But can you say it? Can you show it to everybody? What have you got? So which one is it left hand gold or right hand gold?
Right hand.
So she says that this is gold and this is silver. Is it true? Okay. Everybody says it is true. Okay. So now, how do you know?
I don't know.
Are you going to believe her, or you will want some way to verify it?
I want some way to verify it.
Okay. So now, how will you? Because they are of the exactly same weight and they feel the same. No, you can't open the eyes because you can't do that. Not that. You don't have that option. Okay. So now, figure out how will you do it. Okay. All right. So this is the puzzle for you. And what we'll do is we'll take a small break, come back in 15 minutes, and we'll give an answer to this puzzle. So think about it. So the answer is very simple. He has to only repeatedly ask her what is what, right? And that is the hint to all of you. So we'll take a break. You discuss amongst yourselves. Come out with some strategy to confirm. Yeah, please open his eyes now. Yeah. Is everything okay? Okay. So is this okay? Will you do it? You got the puzzle? So thing is, she is a jeweler and she is managing to actually cheat him by giving 2 silver bars and claiming that one of them is gold. And you have to find a way by which you can confirm whether she is speaking the truth or not speaking the truth. Okay, so this is the task. This can be a group task. Discuss amongst yourselves. We'll take a 15 minutes break, come back and we'll start with the puzzle. Okay. Meanwhile, you also have to be sure, confirm your ways by which you can continue to sell him silver as gold. Okay. All right. So we'll take a break and we'll come back. I think few of you have been able to solve the puzzle. So I think you solved the puzzle and someone else, right? Yeah. So could you please come up with the jeweler and with our customer? Where is our customer? Yeah, please come. please come. So where are our merchandise? Yeah. Okay. All right. So what you have is a, okay. No, okay, okay. So what we do is, so please come. So so now what he has done, I forgot your name, Samarth. Okay. So what Sanmit has done is, Sanmit meanwhile contacted his good friend, Vainavi, who unfortunately also can't see, but she is very intelligent, and knowing the situation, she has found a way by which she can confirm whether the jeweler is speaking the truth or not speaking the truth. So what we'll do is, the customer will now be, can you take out your blindfold? And you wear it, and now she is going to give it to you, and you are going to do what the solution is. Is that okay? Other way around. Yeah, okay.
The other way around.
No, it's okay. It's okay. She knows the answer actually, so it's okay. So it's you who don't know the answer. Okay, and now it's your test. All right, so again, you are going to ask for 1 gold and 1 silver. Go ahead. Where is the mic? Yeah. Okay, all right, so which one is, yeah. So go ahead.
Which one is gold and which one?
No.
Here, no?
Mic is,
Which one is silver?
The right one is gold and the left one is silver.
okay, you wear this. Just 1 minute. Can I put this cordless on you?
You're right.
My right.
So this is gold, this is silver.
Okay, so just show it to people. Which one is gold?
This
Raise
one.
your hand. Okay. So the jeweler says her right hand is gold and left hand is silver. Okay, now you know the answer, but now don't say it. Just see how she finds out whether the jeweler is speaking the truth or not. Okay. And she's saying,
Now tell which one is gold and which one is silver.
is the jeweler caught? Yes. Is the jeweler caught lying? Yes. Yes, the jeweler is caught. Now jeweler is not sure which one is gold and which one is silver. Okay, so make a guess.
The left one is gold.
This one?
Yeah.
No.
Okay, so this was a small puzzle. So congratulations on solving it. So the thing is,
Yeah, so the puzzle here is, yes. Please give claps to all of them.
so now let's this silver bar are yours as a prize.
No, she's the first one, I think.
So she gets 1 silver. Silver bar is your prize for whatever it is.
Yes.
And gold bar is Shantanu's. What?
Oh, they can give that also.
Two? Whom?
You can give it to her and then they can share.
Not gold, not silver. Just a small token.
Yes.
Okay.
Okay, thank you.
So now the thing is, would you explain what the puzzle was?
Yeah, sure. So
Shantanu will explain the puzzle.
So in this case, the old man couldn't see. They couldn't see the color of the thing they had. They had 1 gold, 1 silver. The old man was not, they were blind, so they couldn't see. So this is like, that's a weakness. But even though he is weak, he used the power of randomness. He put the gold and silver behind him, randomly shuffled, and then asked which is which. Now he can repeat this experiments multiple times, and a jeweler cannot always keep lying. Like at one point, she will get caught. So that's the idea.
Okay, so this is one smart way you can catch somebody who is trying to take a wrongful advantage or cheat you. Okay, all right. So now let's go on, and we need a couple of strong people who are strong, physically strong, very strong. Okay. No, just 2 only. To start with, only 2. Okay. I'm going to give you this stuff, and you're going to pull them apart. Okay? Shall I give you the thing? Okay. So, Shantanu, could you prepare the other set?
Sure.
Okay, so these are the 2 rubber pads. I'm keeping them face to face and locking them. Keep them pressed. Okay, and you are going to pull them apart. Just let's see whether you have strong enough. Okay, okay, he managed. Good, good, good. Now let's raise the thing and let's take this. Okay, the same thing. The idea is same. Have you heard of Magdeburg hemispheres? Okay, so this little demonstration is imitation of Magdeburg hemispheres, and let's see how strong our boys are. Pull them apart. Pull it. Pull it. No? All right, all right. Give him a chance. No? Okay, why don't you take one side and he takes another side? All right, all right, all right. More people want to volunteer? Hey, not so many. Wait. Okay. Let two people. Huh? Okay. So you come, you pull from his, you come this side.
Wait.
No. Hold behind him. Yeah. All right.
Okay.
All right. It's okay. Leave it. All right. No, it's okay. You're not weak. This thing is just too strong. Okay. Do we have stronger people?
Sir, what if we twist it? Sir.
Huh? We'll come to that. Breathe. Any boy or any...
Dixit.
Yeah. Is he the strong man? Dixit. Okay. Come. And two girls want to try? Any girl?
Sir, Dixit, sir.
Huh? Dixit. What? Dixit is the name of a student. Okay. So Dixit, you are in demand. Okay. All right. Let's see how strong our boys are. All right. Easy.
Careful.
Easy. You try. You can't. Okay. Sakshat. Okay. Sakshat. Do you want to volunteer? This tiny experiment that we are doing. Okay. No. You guys now sit. You guys sit. We'll try. No. We'll see. We'll give everybody a chance when some other experiment. You want to try this? Meanwhile, you didn't try. You want to try?
Other school children, anybody would like to go?
Are you injured? Are you injured? Is your hand injured? Is there an injury here?
School students.
No. Then you leave it. Wait.
Indraprastha students.
All right.
Okay.
Indraprastha students. Boys are there. Indraprastha.
Okay, you guys sit. You go and sit now. Arey, we have to do more experiments.
Sit. Some of you go, please.
Indraprastha students, please come.
The thing is, you have to pull it.
Please come. It's okay. Please come.
Okay? Yeah. Okay, guys, please sit.
It's okay.
Please sit.
Thank you.
Okay, thank you very much. Any girl would like to try this? All right. Come.
Other than CBSE students, girls of Indraprastha.
Come.
Please.
Come up.
Please go.
It's okay. Come up. All right. The toys, yes. Just be careful. There is power. Just be careful. Okay. No. You have to basically hold it by the handle. No. See, the demo is not that. The
Next,
demo is something else.
Ramakrishna students,
You want to
please
turn
be
this?
ready. You are in high demand
Twist this.
by our President Vasanthi ma'am. Please.
Do it. Everybody should see.
Tenkila students. Please be ready.
For?
Next
2
round.
members. Okay, try.
So wait. Some of you go to the left. Some of you go to the left.
Let everybody be able to see it. Are you able to see them?
Yes.
Okay.
Give some space so we can.
Give some space. Give some space. Yeah.
Now you can do it.
Yeah. Easy. Be careful. Okay, all right. See, the thing is this. Okay, last chance and then we'll tell the answer. It's okay. Hey, girls, it's okay. It's okay. Okay,
Sir,
now it's the time.
Okay. Careful.
Okay.
Sir,
All right.
other school children also
Thank you,
are
thank
also
you.
enthusiastic.
Shall we do it ourselves?
Sir, other school children are also very much enthusiastic.
About this?
Yeah, sir.
All right.
Okay, come.
Come. Okay. So you have to just hold it and pull it apart. Huh? Just be careful. No, you have to only pull. You have to pull. The idea is to pull. Okay, all right. So what we'll do is, we'll play with this toy. You can come during lunch break. Meanwhile, we'll move on. After, at lunch break, you can come back and try your hands at this. And now it's time to tell you guys, like, you are not weak. You are not at all weak. When you were not able to separate it, it does not mean that you were weak. It is just that what we have done is we have created a partial vacuum. Because if we look at this toy, can we focus the camera on this? Excuse me, can we focus the camera on this? On this black stuff. These two things. Okay, so what we did was we kept them face to face and pulled them apart, creating a partial pressure on it. Okay, so the pressure inside the two rubber pads is now less than atmospheric pressure, and atmospheric pressure is acting on it from all sides. So when we are trying to pull it apart, it will require a very high amount of force to separate it. Okay, so this we can do. It's relatively simple because it is very small, the surface area is very low, and the pull is also low. But in these pads, basically the surface area is very high and the pressure created is relatively far lower than atmospheric pressure. That is the reason when atmospheric pressure has been working on it all along, we could not separate it. But now if we put it in some container where the pressure is lower than atmospheric pressure, this will automatically and very easily come out. So this is so much about the air pressure demo. The thing is, any idea of how much is the air pressure around us? We are, right, there is air all around us and it has certain pressure. So what is the air pressure? Yeah, that's about that much, and we are creating lower pressure in that. So what is important is, because of pressure, the variation in pressure can also create weather disturbance, something like cyclones that get created because of pressure difference. So now what we'll do is, we have a very small demo wherein we'll create a tornado. Meanwhile, we'll just do a very small experiment. So we have basically just two bottles that are connected by a pipe. All right. Yeah. So it's just a small connector which is made up of top of these two bottles but with a center hole. And now the idea is, I connect these two things. Okay, so now in our experiment we have water in the bottom bottle, and what is there in the top bottle? Air in the top bottle. And now suppose I flip it. I keep the water bottle up and this bottle down, what will happen? So let's see that. I'm just flipping it. I need to hold this for stability. So can we focus on this part? Can we focus on this part? Yeah. So do you see water coming in the lower bottle? Okay. So now if the bottle has to empty, how much time will it take according to you? This is, mind you, this is 2 liters and we are probably dropping about couple of millimeters per minute.
Some people are saying 1 hour.
1 hour, 2 hour, any other answer? Or what if I say that if I just maintain it like this, it will always be like this. Why should the water come down at all? Yeah. See, the thing is, the people who said it will come down in certain time, what is the reason it will come down? See, for water to come down, air must somehow go into the top bottle, but now air cannot go because all the air path is blocked by the water itself. So, by itself, it will remain like this until we disturb it. Okay? Now, let us say if we have a smart way of disturbing it and create a flow from top bottom to the bottom bottle. So, let me just give it a small twist.
Full bottle.
Yeah, full bottle. Show full bottle.
Video.
And I'll just shake it vigorously and let's see what happens. So you guys see something?
Super zoom.
Just show the top bottle. So do you see a tornado getting created? Okay? So what is a tornado? What are we seeing, what we see? What is it? Any idea? Whirlpool, yes, but why? Do you see that the whirlpool is twisted? Or is it straight? It is twisted, that's one observation. Secondly, is the diameter of the whirlpool changing with the height? Do you see that? And we have it. Okay, so now, why did we create a whirlpool and what does it mean? Any guess before we tell the answer? See, this little experiment was to show effect of pressure and effect of circulatory currents. So we set up a circulatory water current by way of air going in the upper bottle. Okay, and the tornado that got created, how many of you have seen tornado? Have you seen tornado especially before monsoon? Okay, so in a tornado, listen. Does the diameter increase with height? Like, is the tornado narrower at the bottom and wider at the top, or is it other way around? So you always see tornado to be wider at the top and narrower at the bottom. And do you always see tornado going in some particular direction, like always clockwise or always counterclockwise, or do you see any change in that? No. So if a tornado is going clockwise, can it suddenly become counterclockwise? Okay. Why? No. Think about it. So this is one little puzzle for you guys. This tornado you can make at home.
The tornado will be turning in one side, right? Suddenly it can't turn the other way around because it will have pressure, like.
What else?
Force.
From where the force will come? Okay, so this is a little toy that you can build at home on your own and play with it. and you will be able to figure out the answer. That's the small homework we would like to give you for some time. Okay, and now we'll move on and go to the next experiment. Yeah. No, tornado, you think about it. We'll come to tornado after some time. And now what I have is, I have taken three beakers and I'm going to pour some water in it. Only thing is, in one beaker, I have really cold water. Can we just put some more dry ice in it? Yeah.
Sure.
You take the plain water. Okay. So what did I put in the water right now? Dry ice. What is dry ice? And is it cold or is it hot? How cold? Okay, so minus 200 degree. Yeah, can we put the camera on this? On the beakers and no, let it. This is okay. This is okay. And we need some plain water in the other one. Yeah. So okay, let me just put some color. What I am doing right now is, I have taken water in three containers, glass containers. All right, everybody can see this? Okay, so the leftmost is extremely cold. The center one is normal water and this is hot water. Okay, and I'm going to put some color in this. Okay, and let's see what happens. You see carefully what happens. I'm going to put a couple of drops of color. Do you see any difference? What is the difference? Do you see patterns? And what is happening? So are the patterns identical in three beakers? Okay. Any idea why in the beaker with hot water we are seeing it's almost uniform color now? In the normal temperature water, it is still we are seeing patterns of blue and patterns of clear. And in the cold beaker, we are seeing that the diffusion is even less. Yeah. So this is a little experiment called diffusion. So anybody, what is diffusion? Any idea? Where do we experience diffusion in everyday life? Wait. So, go ahead.
So that example you said, like adding sugar to hot water will like dissolve quickly, while in cold water it takes a long time.
Yeah, that's true, but the reason is why. See, we are always talking about a very basic question, why? Okay, this is an observation what you said. Observation is correct. What is the reason? Is it because it is not in a mood to mix, or is it something else?
It is because the heated water is it has more kinetic energy than the cold water.
Okay, that is one thing. Other thing?
Sir, because of kinetic energy, particles of matter are continuously moving. When there is more heat, the movement is more.
Okay. Any other thing? Go ahead.
ಯಾಕೆಂತ ಹೇಳಿದ್ರೆ ಅದರಲ್ಲಿ ಈಗ ಬಿಸಿ ನೀರಲ್ಲಿ ಕಣಗಳ ಚಲನೆ ಜಾಸ್ತಿ ಇರ್ತದೆ.
Yeah, but see, the question is why? What is this process? So this is basically a little experiment of diffusion. Diffusion is something we all experience every day unknowingly, because the process of oxygen mixing with our blood is process of diffusion. Okay, let me say it again. When we breathe, what do we breathe? We breathe air, not oxygen. Okay? Just remember, our nose has no way to distinguish air from oxygen. We always breathe in air. What happens in our lungs is oxygen mixes with the blood through a process called as diffusion. So this tiny experiment was an experiment of diffusion wherein the color diffused in the hot water. Okay? So when we breathe air. From what we breathe, it's only about 3 to 5% of oxygen in a single breath that actually mixes with the blood. Rest all is given out when we exhale. So when we exhale, our exhalation, the way it is presented that it is carbon dioxide, it is carbon dioxide plus other gases including air and moisture. So remember, whenever you read this in textbook that animals exhale carbon dioxide, it has to be taken with a bit of correction that along with carbon dioxide, the amount of air that was taken inside the lungs at the time of breathing in is also exhaled. Okay, so just important thing, do remember. So this was a tiny experiment about diffusion, and now is it time to play with the balls?
Yes.
Okay, let's take some balls, and sir, we have a football.
Just a minute, sir.
Yes. Oh, the break. Okay, all right.
Ramakrishna students can go to planetarium now. Ramakrishna students can go to planetarium now.
Let it. We don't need the space for anything else. Right? So, okay. So what we'll do is we'll take more balls. The balls are here in the smaller bag.
5th A students also, those who did not get that chance, now they can go. 5th A students, those who did not get the chance that time, you can go.
So how many of you play cricket? A lot more. How many of you play football? Okay. And girls don't seem to be playing football or cricket. See, remember we just won the World Cup. Remember. So girls also should play in the field. All right. So we have this tiny experiment wherein we are going to drop the balls. So we have a football. It bounces this much. Do you want to try this?
Yes.
Let's see how much does it bounce. This much. You take this ball. Let's see how much does it bounce.
No bounce.
Okay. And what about this ping pong ball? Somewhat. Okay. All right. So now, what Shantanu likes to do is, he wants to keep one ball on top of another and see what happens. Okay? So, ready? What you have to do is, you just hold it like this and drop both the balls simultaneously. Are you ready? Okay, now let's make a prediction. Will the football go up to the ceiling? Will the rubber ball hit the ceiling? And what if he keeps other way around? Let's see. You drop the thing. Let's see. See, individually the bounce is only this much of both the balls. Drop it. Okay. And now when you drop it together, let's see what happens. Okay, all right. Never mind. All right. I think you are at a risk. Okay. Let's do it this way. Okay, what happened? Let's take other ball. Okay, so what is the reason that the balls are experiencing an increasing bounce? And now just for the experiment's sake, would you keep the bigger ball on top and smaller ball at the bottom? The rubber ball. And yeah. See, experiment is same. He is dropping objects of two different sizes from a certain height and trying to ascertain the difference in the outcome. Okay, go ahead. Nothing. All right. So, let's do this rubber ball thing one more time. Give him a count. Come in front. Come in front. Yeah. Drop it. All right. I think. Let me try. Let me try my hand. Okay. Again, the same experiment. A smaller ball on top of a bigger ball and dropping the thing together. And it seemed to go distant. So now the thing is, good catch. All right. So now, why did we see what we saw? Thank you. So now comes the physics. See, remember, we are going to play and find the physics behind it. Play is important, but physics is equally important. So any idea as to why did we see this difference? See, remember, when the smaller ball was kept lower, that time just see whether the big ball took an equal bounce. There was hardly any bounce. Right? Thank you. So now, could you pass that ball? All right. If you said, go ahead. If you give the correct answer, you get a prize. And what would you prefer? This ball? All right. Go ahead.
That football ball, if we keep that rubber ball up of the football ball comes down and bounce. So the pressure will come up and the ball bounces.
That's an observation. But what is the physics? Can we discuss the physics?
Yes.
Yeah, go ahead.
When the football comes down with the rubber ball, when it bounces to the ground, then it pushes the rubber ball, then it goes high.
Yeah, but then why is it going to such a big height? See, remember, when the ball is bouncing off the floor, it is bouncing only this much. But when it is bouncing off the bigger ball, it bounces. It bounces a lot. You see the difference. What I am trying to show is, look at the experiment. We are trying to drop the ball. It bounces only this much. This one bounces only this much. But when I drop them together, so can you give can you guess the physics? Thank you. Yeah. What?
The pressure of both is added.
No, where is the pressure? Yeah, the one in the beer. Could you please come in front? Come and sit in front. No? There are seats in the front. The one in the red t-shirt. Yeah, he has an answer, I think.
When the smaller ball is kept on the football, as the football touches the ground, the momentum of the football gets transferred to the smaller ball. Hence, as the mass of the smaller ball is less, it gains additional speed, hence launches high up into the sky.
Okay, so that's actually the correct answer. Let's give you a big hand. See, what is happening is, we are looking at what is known as, could you please come a bit front and you can collect your reward. A small reward of a cricket ball. Thank you very much. And now, let's look at the science. So basically, when we are dropping it, what it gains is something called as a momentum, which is a product of its mass and velocity. Okay, this ball is lots heavier and we are dropping it from a considerable height, so its velocity gain is also a lot. And relatively, the small ball is much lower mass. Can we just measure the mass? Do we have some things to measure? I think we have a balance. So let's look at the weight of these balls. We have a very tiny balance. Let's see if we can weigh these things. Okay, so this is going overload. So this is more than 200 grams. Our balance can measure up to 200 grams, and this is about 90 grams. So this is more than 200 grams, and this is just about 90 grams. So you look at this, so mass into velocity of this gets transferred to this, and that is the reason it gains a lot of momentum or energy, and that is the reason it bounces to the greater height. So this is about our linear momentum. Where else do we see linear momentum thing working? Do you guys play carom? And you always have a striker. And then there are coins. And you are trying to hit the coin with a striker. What if you reverse it? Suppose you reverse it. you try to hit the striker with the coin, what will be the effect? Is the striker heavy or the coin piece heavy? Piece is heavy. Striker is heavy. And also it is smooth. Right? The surface, the lower surface of the striker is very smooth. Now why is it smoothened? It is smoothened to reduce what is called as friction. Okay? If the friction is less, when we give it a kick, it picks up a momentum or speed, and when it collides with the coin, the momentum gets transferred to the coin and the coin can go wherever depending on the direction. So now another important observation is what happens to the striker. You see, we are playing carom. I hit the striker. Striker goes and hits some coin. But then what happens to the striker's own motion? Does it come back? Does it go? Where does it go? It can come to the stop. And what if it, before coming to the stop, will it come to the stop at the moment of collision? Or will it come to the stop after some time? After some time. So in that much time, the striker moves from its collision place to some other place, right? So how does it move? Yeah, so the total distance covered is much less than the distance covered by the coin, right? Now why this happens? Because the momentum of the striker is transferred to the coin. So the striker itself has very less momentum left with it. That is the reason it traverses less distance and the piece goes to much farther distance. So this so much so about linear momentum. And now let's go ahead and next experiment. Shall we play with magnets? Okay, all right. So let's see this. Now I need 3 volunteers.
Our students are not supposed to come. Please come down, children. We will give chance to some other school also. Please come. Please
okay,
come.
one of you.
Please come down.
All of you have been to the stage earlier, right?
Yes, sir. Yes, sir.
Okay,
yes,
so
please come down.
Okay, so you
Please
can. One of you can stay as an observer.
Tenkila students, Tenkila girls, Tenkila students, can you please come fast? Come fast, children.
Okay.
Please come
Both
fast.
of you can stay. All right.
Tenkila
So can we have some girl volunteer to do our tiny experiment?
Tenkila boys, please go.
Please come.
Please come fast.
Can we have some girl volunteer? Any girl would like to do experiment? Come on. Come.
Girls of other schools, please come.
Yeah. Please be quick because we have to do more experiments. I think 3 are enough.
I think it's enough. Thank you.
3 are enough. Oh, we'll call you later. You can be in front. Okay. So what you guys do is this. Please hold 1 tube each. You can also hold 1 tube. You please come this side. No, you give him 1 tube. You want to answer the call? How? You answer the call. Please, you take it. You please face the people. All right. And you have to take this, both the pieces, and drop in their tube, one at a time. Okay. Just see what is happening. Where is the other piece? Okay. It fell down. So now, could you do the same experiment in this? So this experiment is what they have. Let me just please give it to me for a moment. So we have 2 pieces. One is a magnet, one is a non-magnet, but of almost same size and same mass. And we have 3 different tubes. One is of copper, one is a plastic, and the third tube is, what is this material? Can you see it? No, this is not iron. This is aluminium. Okay. So we have 3 different tubes made of 3 different material. One is copper, one is, what is this? Plastic, and this is aluminium. Okay. And our volunteers, they are going to drop the magnets and the non-magnet in everything. And we are going to look at the time it takes for the piece to fall. Okay. So one at a time. Please show it to people. You stand like this. Let everybody see it. Okay, go ahead. Okay, so one thing came out fast. Another one is taking. And okay, all right. So this time, now could you drop the things in plastic? So you look at the time it takes for both the things. And here it's almost the same, right? And now could you drop the things in the other tube? Yeah. So bit longer, and this came out much faster. So what did we see in this experiment? Okay.
In the metal tube, the second one came very late.
So the magnet took longer,
Yes.
and the non-magnet came relatively quickly.
Yes.
And in this tube,
Both came in the
both
same
came
time.
took almost the same time. And in this tube,
And the first one took more time.
magnet took long. But did it take as long as it took in copper, or was it different?
Was it different?
Yeah. So was it more or less?
More.
It took more in this?
Yes.
Okay, let's do it one more time. So right now what she says is, so please come this side. So what she is saying is, as an observation, they observe magnet taking longer time to come out of the copper tube, or shorter time. It took longer in aluminum, right? Okay. So let's time it. So you give her a count, 3, 2, 1, and count the time. So at their count, drop. 3. Drop it. Okay, and now please drop it again in copper. Let's see which tube takes longer. So copper is taking longer, right? Yes. Okay. So now the question is, okay, thank you very much, volunteers. Thank you. Yeah. Okay. So
Thank you.
So did we see the experiment? Did you see the experiment? So in this experiment, what we did was we took 3 different materials of different electrical conductivity, and we dropped a magnet and a non-magnet, which is, they are both of almost same size and same mass. And then we are trying to look at the time it took for the material to come out from the other end of the tube. And what did we see? Did we see the times different, or were the times same? Different, but only for, and for a plastic tube? Same. So now here comes his favorite question. Why? See, why is the question that you have to ask? You observed the experiment. Now, why? Why was it the way it is? Everybody is convinced with the experiment? Or was there is there someone who thinks the experiment is erroneous?
Did you do something to the copper so it goes slow?
That's a valid doubt, but I don't think copper is copper. I have not done anything to the copper. You can take any other copper piece and do the experiment. Okay. So everybody observed the experiment, right? Everybody has seen it took much longer time for the magnet to come out of the copper tube as compared with that for the plastic tube or even the aluminum tube. So the question is why?
Sir. It is because of eddy current.
Okay. So what is happening? What is eddy current?
When the magnet falls through the conductive material, it generates a current, and the current generates a bit of power. The power is and that power generates a magnetic field again, which is the opposite of, which opposes the motion of the magnet. So it slows down.
Okay. But why did it happen differently in copper and aluminum? Both are conducting.
But copper is more conductive than aluminum.
And what about this?
Plastic is not conductive at all. It is an insulator.
So there is no eddy current setup in this?
No.
And suppose I decide to cut this copper tube into, I give it a cut. Yes. Then what will happen?
It won't. It won't slow down.
It won't slow down. So basically you are saying that the eddy currents won't get set up.
Yes.
Okay. So that's absolutely correct. And as a small reward, we give you also a rubber ball. Can we just give him a rubber ball? Are you in the 11th class, 12th class? 8th class. Okay, good. What's your name? Okay, so Aditya gets a small reward. Thank you very much. And play with it. Okay, so let's move on. So the thing is, the so-called eddy currents, where do they matter? We saw this experiment, we saw the currents getting set up. The reason that he gave, that copper has higher conductivity and hence more currents will flow, and more current will mean a stronger magnetic field, and that's why magnet took longer. That's actually a correct reason. But now, what happens? I mean, where do we see it? So have you heard of magnetic braking? Have you heard of this term called magnetic braking? So would you like to see a demo of magnetic braking? Okay, so for that, what do we require? Do we have it? I think we have it. So what we do is we take a magnet and we make a pendulum out of it. Okay, please give us a minute till we find the thread. Yeah, I got it. Okay. So let's make a pendulum. What is a pendulum? Anybody? A mass that is hanging off a string, right? Have you seen it? Okay, so can we take some cello tape? We have some tape here or something to tie it. Yeah. Let's tie this up. And our pendulum will be ready. Okay. All right, so our tiny pendulum is ready. And is it oscillating freely? Okay. Now all that I want, Shantanu, is we have a small plate of copper. Yeah. Okay. So this pendulum is oscillating very freely. And can you bring this plate closer to the magnet and not actually touch it? You don't have to touch it.
From below, no?
Yeah. No, from side. Or you take the pendulum. You move the pendulum. Just give it a very large swing. Let it swing. Yeah. Give it a large swing. More. Yeah. Swing it. So is it swinging? Okay. Now just hold it. And now let's see if we can slow it down without touching with the help of this copper plate. Do you see it suddenly stopped? Okay? Yeah, shall we do it again? Give it a swing. No, this is okay. It's just that I think I'm not able to get the right position of copper. You hold it steady. And then suddenly it sets into rotation and its amplitude is dropping. Right? Now, do you see magnet rotating? And again the favorite question. Exactly. Why? See, it's still rotating. Are you pushing it? Are you twisting the thread?
No.
Is it twisting the thread? Okay, and then it has eventually stopped. It will take some counter turns. So what is happening? All right, so you guys think about it, and we'll come back to this experiment in some time. And meanwhile, let's go ahead and start with, do you guys like to roll things? Okay. Now let's start rolling the things. Suppose we take different objects. Let's say that this is my inclined surface and I keep it inclined by way of keeping the table on top of my bag. All right. Yeah. Is it very sharp incline? All right. So right now we have some inclination and we'll try to roll things on top of it. And to roll, what I have is basically an empty bottle, a bottle that is half filled with rice, and I think we have one more bottle that is filled with something else. Yeah, I find it. Here. Okay, so I like to roll things, or Shantanu likes to roll things, and what he has found in his home, 3 bottles, they are normal plastic containers, As an experiment, in one container, he has not put anything. So what is there in this container? Air. Okay. All right. So he has air. And in this container, he used to play pebbles.
Yes.
Do you guys play pebbles?
Marbles.
Huh? Marbles.
Marbles.
Marbles. Do you guys play marbles? All right, good. So it's still in thing. I thought this was only my childhood thing. All right. And then he's going to roll the things. So if he has to make a race of these two things, which one do you think will reach earlier? So let's see. Let's see. So hold it. Yeah. So will you give him a count? Okay. Just. All right. No. Before that. How many think that the heavier or the bottle filled with marbles will reach earlier, and how many think that this empty bottle will reach earlier? How many think this bottle will reach earlier? Empty bottle. Just listen to the question very carefully. This bottle you think will reach earlier? And how many think this bottle will reach down earlier? Hey, some people are raising hand for both the things. How can that be? All right, so let's do this experiment. And now you give Shantanu a count, and at their count, you just lift the thing. Can you focus on the thing? Could you focus on the bottles? Yeah. All right, 3. Go. And the heavier bottle came down first. Okay. All right. Thank you very much. Now let's change the thing. Now in this experiment, he has decided to take heavy bottle or the empty bottle with a bottle that is half filled with grains. Now which one do you think will reach first? This bottle or this bottle? This bottle will reach first. And will this roll? It will not roll. It will roll. Let's see. Again, please give him a count. Okay. So now let's change our experiment a bit and change the angle of inclination. Let's reduce the inclination a bit. So to do that, what we have is how do we change the inclination is, yeah, we'll use the smaller bag. But I think it is almost the same. No, we can change it. Yeah, now it's certainly different. Okay, now the inclination is different, and let's roll the bottle one more time. This, and let's take the empty bottle, and let's see this. Yeah. Release. What happened to this? Why is it not rolling? Is it moving or is it stable? Why is it stable? Gravity is on this bottle as well. But then this bottle is lots heavier and it rolled down. उससे क्या होता है? Could you come on top? Take the mic, take the mic. Yeah. Say it.
Because of the grains half filled, the friction of the bottle comes less and.
But where is the friction? See, basically the surface is uniform. It has the same surface as compared to this, right? In our earlier experiment, we saw that heavier bottle rolls down much faster, right?
Sir, because the bottle is half filled and the weight is down, and if it turns once, then it will turn continuously.
So if I give it one full turn, you think it will roll completely? Let's see this. You can roll it yourself. Come. It's okay. Come. What happened? Give it one more push. Yeah. So why? See, everybody saw the difference, right? Is this bottle rolling at all? Okay, now the question is why? See, is it a magic? There is science, yes? So, give him the mic. Yeah.
Because
Go ahead, say it.
Means the slope became a little down and it don't has more force to come down, and half is filled, so it needs more force to rotate one and another.
So that means if I raise the height, will it roll? Let's see. Is this? Yeah. So now what happened?
Now the slope becomes more down, and the force is the slope is enough to push the.
So basically, the idea is the grains within the bottle must move.
Yeah.
Right?
Yes, sir.
So the weight should get transferred in front. Yeah. So that's correct. So in this experiment, what was happening? Thank you. And what do we have? We can give you also a small rubber ball. I think they are in this bag. Okay, this is a small reward to you. Okay. So the thing is, you must have seen dumpers parked on road, and they are half filled and they are stable, right? So here this bottle was not moving at lower slopes because the grains were not rolling forward. So the pressure, the force that was net downward force was far more than the net force experienced in the horizontal direction, and that is why this bottle remained steady. So remember, you should, when you are thinking in terms of for objects like this in classical mechanics, should always think how the force is distributed. Okay, so this was our tiny example of distribution of force. And now let's go ahead and do one more experiment of, shall we do a friction experiment? What is the friction? Force that opposes the translational motion, right? So now I have two notebooks. Where is my other notebook? Yeah, I found it. And now let us say that I mix their pages, I intersperse pages like this. Could you just help me? Yeah. Okay. So some random mixing. Okay. So Shantanu, can you just pull the books apart? Can you pull the things apart? No? No? What is happening? Friction, but where is the friction? What friction are we talking about? See, I'm keeping it horizontal and just trying to pull it apart. How? What friction? And how did I manage to do it? And whereas he was not able to do it. So everybody has notebook at home? Okay? So when you go home, just make sure that you are mixing the book like this, pages like this, and try to pull it apart. Okay? So similarly, so just try to pull it apart and see if you can. Sometimes you will, sometimes you will not, and you have to think why you could and why you could not, both ways. Now with this, after this tiny friction experiment, I think, are we ready for next part? So next part should be what? What shall we do? Liquid nitrogen. But I think you have seen liquid nitrogen. All of you have seen liquid nitrogen. So do you want to see it again? Liquid nitrogen. Let's not do liquid nitrogen. Let's do something else.
No, let's do it.
And then let's come back to the nitrogen.
Okay.
So what shall we do? Do you have balloons?
Yeah, we had balloons.
We have balloons? Do we have balloons? Do you guys have balloons at home? Okay, so let's see. We have some balloons here. And the balloons are in the pressure cooker. Nice way to store balloons, right? So I need couple of volunteers to blow the balloon. Hey, be there.
Wait. No? This side, I think, right? This will go.
Volunteers, anybody here?
Okay, for the time being, this much is okay. Are you able to do it? No? Okay, all right. So I think Shantanu will manage to do it. Shantanu, could you blow it up?
Next,
All right.
Manipala School,
Thank you very
Tenkila
much.
Kannada Medium, and Ambika students are going to watch planetarium. So now
All
it's
right, thank
better
you.
to
You can
have
sit.
lunch, and our volunteers will take you.
Okay. all
Ambika
right.
students,
Just tie a thread to this.
please come.
Tie a thread to that. And
Ambika students, please come. Indraprastha students, please come. Vivekananda Kannada Medium students, please come. And Manipala students, please go and have your lunch first. Our volunteers will take you. Please go and have your lunch first, and then you can come for
small length is okay.
planetarium. Please maintain silence there. Please maintain
Okay.
silence there. Vivekananda Kannada medium students only, not English medium students. Vivekananda Kannada medium students only, not English medium students.
Okay. All right.
Please go and have your
So-
lunch now.
I have these tiny balloons, and if Shantanu blows between these two balloons, what will happen? Will they come close or will they go apart? Let's see. So you have to blow between these two balloons. I'm holding them close. You can take a pipe. You can blow through the pipe. The plastic pipe that we had for the experiment. Yeah, or aluminum. Take anyone, and you can use the pipe to blow. So the experiment is very simple. He's going to blow between the two balloons, and we are going to see what happens. No, wait. Let them stabilize a bit. Okay, all right. Now.
Vivekananda English medium students.
So what
please
is
be
happening?
seated here.
Is he able to separate the
Please
balloons?
be seated here.
See, to start with, there is a very small gap. All right, now blow. And when he blew, when he's blowing in between the balloons, they are actually coming close. Did you see that? So, why? Why did they not go away from each other but came closer? What is the reason? Technology. What technology? Anyone in back? Yeah, go ahead. Or any girl? Any girl has some answer to this?
You want to say?
See, the thing is very simple. What we did was we took two balloons and kept them about an inch away from each other, and he's trying to blow in between the two balloons with an expectation that balloons will go farther away from each other. But in the actual experiment, they came closer. Rather than going away, the balloons came closer. So, yeah, go ahead. Somebody is saying, yeah.
When a force will come, that balloon will come together.
Which force?
That when we will do.
No, he's trying to blow. So he's applying force between the two balloons with an idea to drive them away, but they are actually coming close.
When outside air will come together, that balloon will come together.
That's okay, but see, thing is, he's blowing the air. What he's blowing is he's blowing the air only. You got the thing? Shall we do it one more time? Okay. See, the thing is, you're partially right. Hello, young man. You're partially right. And what is happening is, when he blows, he's actually creating a reduced pressure between the two balloons. So when balloons are like this, the pressure around the balloons is all through the same. But when he's blowing in between the balloons, the pressure between the two balloons slightly drops. which makes the surrounding to force the balloon towards each other. Is that what you are saying? Is that what you are saying? Shantanu, could you say it? No, you say it in Kannada to him. Na? She is not probably getting it.
What he was saying will put a force between them or something like that.
No, I think you could you speak it in could you say it in Kannada? No, from here, Shantanu. You say it in Kannada for he gets it clearly.
So ಏನಾಗ್ತಿದೆ ಬಲೂನ್ ಎಕ್ಸ್ಪೆರಿಮೆಂಟ್ ಅಲ್ಲಿ ಅದು ಬಲೂನ್ಸ್ ಯಾಕೆ ಒಟ್ಟಿಗಿದೆ
when we will put pressure to that balloon, that will come together.
ವಿಚ್ ಪ್ರೆಷರ್ ಅಂದ್ರೆ ಎಷ್ಟು ಪ್ರೆಷರ್ ಹೈ ಪ್ರೆಷರ್ ಲೋ ಪ್ರೆಷರ್
Low pressure.
ಲೋ ಪ್ರೆಷರ್
So pressure between the two balloons is low. That's what you are saying. Is that what you are saying?
Yes.
Okay. Yeah, that's actually correct. So you are right. You are right. Okay. So little thing about pressure, and now I think he is here. I think he is here for a reward. Reward? Your reward is balloon. Thank you very much.
Thank you.
And now, shall we do liquid nitrogen? Okay, let's play with liquid nitrogen. Okay. So, how many of you have seen liquid nitrogen demonstration earlier? Okay, all right, great. So, what is liquid nitrogen? What is liquid nitrogen? So, if I what is it? Let's do it one more time. So, what makes liquid nitrogen great is it is one of the coldest liquids available to the mankind. And how much nitrogen is there in the air? Okay, so that means it is abundant, right? We can easily get gas from the air and liquefy it, and we get what? Liquid nitrogen, correct. So this is what liquid nitrogen is. So what is the temperature of liquid nitrogen? How much? Minus 200, almost. Actually, it is minus 196 Celsius or 77 Kelvin. So that is the temperature at which nitrogen becomes gas. And also that means that we have liquid nitrogen at same temperature, boiling at same temperature. So we have this thermocol container in which we have taken some liquid nitrogen. And now let's play with it. Suppose I put this balloon in liquid nitrogen, what will happen? Will it break? Will it become big or will it become small? If I dip it in nitrogen, will it become big or will it become small? How many say it will become big? There are people who say it will become big. Okay, let's see. Now, see, be careful. I am not putting my hand into liquid nitrogen because my hand will break if I put it in liquid nitrogen. And I don't want to lose my hand. Do you want to lose your hand?
No.
Okay. Any one of you want to lose the hand? Okay, good. Don't. Okay, let's see. Is it becoming big or is it becoming smaller? Shantanu can see it.
It's becoming smaller.
Let's try to dip it more. And we have some straw or something. Okay, let's put some. No, it's okay. We have this. Let's see what this balloon becomes. Okay. See, this is what has become of that balloon. And now you see that it is gradually, is it becoming bigger? Why is it becoming big? Because there was air in the balloon, and when we put the balloon in liquid nitrogen, the temperature of the air also fell. And now we know that if the temperature falls, volume will also decrease. Yeah. So that is the reason the ball crumpled and there was surrounding pressure. So the ball crumpled, and now you see that as the balloon is warming up, it is slowly becoming big. Do you see anything dark inside? At the bottom? Do you see it? It has, yeah, some powder-like thing? Yeah. What is it? No, no, no. No, 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 no. No, no, no. It is not nitrogen. No, 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 no. No, 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 no. Think. Certainly not water. Where will the water come? See, ice of what? Ice of nitrogen will be at what temperature? See, 196 Celsius minus is the temperature at which nitrogen becomes liquid. To become ice, it will have to be cooled further. At what temperature does water become ice? 4 Who said 4 degrees? 0. Okay, so that means for water to become ice, it has to be cooled further, right? Because at 100 degrees centigrade, which is the boiling point of water, do you have ice at that temperature? Okay. So that means if you have to make solid ice, you must cool liquid water to much lower temperature. So such a temperature for nitrogen is 55 Kelvin. At 55 Kelvin, nitrogen can become a solid nitrogen. But do we have that temperature? We don't have it. So what was it? From where did the carbon dioxide come? But we put air in this, right? So where did the carbon dioxide come in this? I think you are just making guesses. You are just making guesses. All right. So fine. Let's leave that at that. And now let's see what happens if we start putting things in liquid nitrogen. So we have some tiny stuff. Let us see this. Let us see if our torch is working. Yeah. All right. So are you guys able to see the light on? It's very faint. Let's have some dark background. Yeah, it's very faint. And so now my battery has a small coil of copper connected in it. And now let me just try to cool this copper and see what happens to the brightness of the lamp. Is the lamp glowing brighter? Can we have the dark background?
Grade 6 students.
Is it glowing brightly?
Please go to planetarium. In a line.
Okay. Now if I take the coil out, will it lose the brightness again? Let's see. It's not. Or is it slowly losing it?
It's
losing it slowly. So anybody who can explain why is it so? We saw the experiment, right?
Atreya.
So what is happening is when I put the coil in liquid nitrogen, the resistance of copper reduced. It is not zero, it reduced. And that reduction meant that more current could flow through the lamp, and hence we got higher brightness. So materials, especially metals, the electrical resistance reduces when we cool them to lower temperatures. And as we heat them, the electrical resistance goes up. Now let us see if we have something more. And yeah. So what I have is some magnets. And I have one more material which I would like to cool and see if it can float over the magnets. So for that, I have my tiny thermocol tray and I'm going to put some nitrogen in it.
Seventh girls, form line and go.
Let's see. So we'll allow it to cool for some time and then we'll place the thing on magnets and see if it can float on the magnets. Okay, that's our little experiment. and we'll try to reason why we see what we see. Okay. Piece of paper will do. Paper. Piece of paper will do. See, I'm not putting my finger in liquid nitrogen because if I put, I'll lose my finger. So I'll use a tiny spoon made up of paper to lift my material and hold it above the magnet. Do you see it floating? Can you just focus on this? Okay, it will fall. Let's cool it again. So keep it focused on the magnets. Is this better? Yeah. Is it floating? And it will slowly drop. Okay, now why did it float and why did it drop? Any idea? So what this material is, this is something called as a superconductor. A superconductor is a material that is a perfect diamagnet. We know that if we take magnet close to iron, it attracts, right? So that is ferromagnetism. So like that, there is something called as diamagnetism, which means that material will get repelled from the magnet. So there is an attraction, also repulsion. So when superconductor is a perfect diamagnet, in the sense that whatever field we apply, it will create an equal field in it, which will oppose the applied field, and that is the reason we will see the material floating. Okay, so as long as this material is superconducting, that is very cold, it will become, it will float over the magnet and eventually it will drop. Okay, so much so about liquid nitrogen, and it is almost the closing time, and I think Shantanu, you will have one more puzzle. Okay, so we'll give you one more puzzle to think about, and we'll take questions and then we'll stop. Is that okay? Are you guys hungry? Okay, they are hungry. You are not hungry. Okay, so he is hungry, I am hungry, we'll take a break, we'll come back at 2 and you please be back at 2 o'clock. But before we break, there is a small bit of homework in the form of puzzles.
Okay, can I have one volunteer who wants to come? So, what's your name? Akshay. Okay. Do you stay in a hostel or something? Okay. So Akshay stays in a hostel. So in the hostel there are 10 rooms that you can see, 1 to 10. So what Akshay does is, so he goes from door number 1 to door number 10, and he will flip every door. So if a door is closed, he will open it, and if it's open, he'll close it. So in the first round, he'll go from door number 1 to 10, and he'll flip all the doors. No, do it. No. So flip this, then you go to the next one, then again. Okay, maybe just a minute. Maybe we'll do it for 5 doors first so that it's easy to understand.
So just pay attention as to what he is doing.
Okay.
One fine day he is very bored in the hostel, and he wants to just keep everybody's door open if it was closed, and he will close the door if it was open.
Open, yes.
Okay.
So in the first round, what he'll do, he'll go from door number 1 to door number 5, and he will open all of them. Now what he will do, he'll come back to the beginning, and now he will flip every second door. Done. Now he'll again come back to the front and he'll flip every third door. Okay, done. Now every fourth door. Now fifth door. Okay. Now this is with 5 doors. We can do the same thing even with 10 doors. So try to do with 10 doors. So the first round he will flip every door. The second round he will now go and flip every second door. So in the third round he will flip every third door. 3, 6, 9. In the fourth round it is all the 4 doors, 4 and 8. The fifth round you flip 5. Sixth round you flip 5 and 10, correct. Sixth round you flip 6. Seventh round you flip 7. Eighth round you flip 8. Ninth round you flip 9. 10th round you flip 10. Okay. Now at the end you are seeing door number 1, 4 and 9 are open, correct? Okay. So now the question is, suppose I do the same thing for 30 doors. I do the same experiment. We don't do it here. So if you do it for 30 doors, which doors will be open at the end? So did everyone understand what the puzzle is? Okay. So the question is, if you do this process from 1 to 30, at the end, which of the doors will be open? Think about it. Thank you.
Okay, so now we'll take questions about whatever we presented or even otherwise. And go ahead. So please raise your hand and mic will come to you. Can we have a volunteer to take the mic?
Sir, that time you said about that example, right? That big ball and a small rubber ball. When we put it down, the ball will go to the ceiling. That what if we what if we keep 2 balls upon that football?
So basically what you are saying is a big ball, a small ball and another small ball.
Yes, sir.
You can do it. You can do it. What will happen? You think it's just an extension of what we did?
Sir, answer about that. 1, 4, 9, 16, 25.
Here?
Yes.
That is correct, but should we do it after the break or now?
Yeah, but we'll reason after the break.
Yeah, but your answer is correct.
Your answer is correct. So think about it. You will get it. You will get it. If not, you can always experimentally verify what you think. Okay.
Who next has to answer?
Yeah, I think here.
Sir, how is liquid nitrogen made?
Okay, so liquid nitrogen is made, so what you do is you take air and from air you remove all gases except nitrogen. Okay, then you have what is almost full pure nitrogen. You allow that gas, you compress that gas and allow it to expand and then you do it repeatedly. So this process, because of this process, the gas loses what is called as the internal energy of it and it effectively cools and becomes liquid. So you do it multiple times, this cycle, something called as, what's that called as?
Tenkila English Medium School.
So
Tenkila English
So that's
medium.
the way one removes the excess heat from the gas and it becomes liquid.
Thank you,
Yeah.
Sir, that time you showed, right, that when to roll those
Bottles.
yeah.
Ha.
Now you said, right, that half filled rice. When we tilt it a little bit like this, then the filled rice bottle will not go down. It will be stayed there.
Half filled, yes.
What if we fill that bottle full?
So do it. So that full bottle will be very similar to our bottle with marbles. So what you are asking, if I get you right, if the marbles are replaced with rice, will the effect be the same? Is that what? It will be the same. See, what is happening in this experiment is when we take where is our half-filled bottle? Okay, yeah. So what is happening in this is, when it is at an inclined when it is inclined like this, if we have to think in terms of force acting on the bottle, so there is one force acting in this direction, in the direction of motion, and there is another force which is acting vertically downwards. So if the vertically acting downward force is more than the force in this direction, then it will not be able to move, right? So what was happening at certain inclination is the force acting downwards was far more than force acting in this direction, and the rice was not able to roll over. So that means there was nothing dynamic, nothing changing with time. So that is why the bottle remained like this. That's the reason. Okay.
What will happen if we put the football to the liquid nitrogen?
Well, we'll lose the football for sure, because there is one more tube inside this, right, which is a rubber tube, and this is stitched. So the thread may not be able to withstand lower temperatures, and it will certainly become small. But when it becomes normal again, the ball may not remain playable, unlikely to remain playable. That's the only thing.
Okay, sir.
Okay.
Now, the first session we can...
Okay, maybe shall we end, or you have some question? If there is a question, you can come back after lunch and we'll be here. Okay? So thank you for your attention, and be curious and keep pushing. That's the message from us. So thank you from me and Shantanu. Thank you for your attention.
Sir, thanks a lot for the enthusiasm that you produced in our children, and they're very happy and very enthusiastic to know about our basic science. For the first session, we are very much thankful to you.
Thank you. Ready? Okay, so let's begin with the chalks. And are you ready with the chalks, Shantanu?
Yes.
But this time, how many of you were here in the morning? Quite a few of people were here in the morning. Okay, so we'll do newer experiments as much as possible. And camera, can we focus on what is in the trays, these plates? It may be a bit difficult. So what I'll do is I'll place them on the floor. Okay, so I have chalks in my hand, and you see different colors in the plate. So any guess as to what we are going to do? So, chromatography. Okay, so what we are going to do is called as chromatography. Can I have one more chalk?
Sure.
Chromatography. Chroma is color, and graphy is, you can say, saying it in context. So what I'm going to do is, as a part of this experiment, I have 3 white chalks, and I'm going to put 1 chalk each in 3 plates. So here goes 1 in green. It has to stand. Okay. 1 goes in red, orange, and the third one goes in red. Okay. And we are going to wait for some time and see what we get on the chalk. Okay. So do you see something? What is happening? So
Color is slowly coming up.
yeah, but is the shade same as that in the paper tray? Okay. So in the leftmost thing, the red one, what color do you see? And in the center? And in the rightmost? And that's the color of the water. But what color do you see on the chalks? So what we'll do is we'll allow this to stay for some time, and meanwhile we'll move on with to the next experiment, and we'll come back to this after some time. Okay, and see what we get. So let it stay. Let's come back to this experiment, and meanwhile let's go and do something different now. Let's take some water, and can you give me a glass? A transparent glass. And can we bring the focus back on the table? Yeah. And let's start pouring water in the glass. So where do you see the meniscus, water meniscus? Is it flat or slightly curved? How is it? Yeah. It's shaking too much. Okay. So one thing is, it should not move, so we cannot walk. So let me start adding water to this. How much water can I add? Okay. Do you see it bulging? Do you see a top curvature now? So can I add more water or will it immediately spill over? What will happen? Shall I pour? Okay, or let's take a dropper. Can we take a dropper? The dropper is there. Is there. Below the papers. Below the papers. Yeah. So to get good control over adding the water, I'll start using a dropper. And let's see how much water I can add. Did it spill? But do you see a top meniscus, top layer, curved layer? Okay, let's try to add more water. Okay, so what is it? Because normally what we see or what we read in textbook is water level typically remains flat. Is that correct? Or not correct? Correct. But now here we are seeing that it's not flat, but it is curved. Right? So why is it curved and why is it still maintaining the shape? And let me try to add more water. I have about half dropper full and let's see how much I can add. Okay, it's still holding. It's not spilling. Let me take some more water. Do you see it? Are you surprised? So, now if I say that I can try and float a blade on it, will you believe it? Okay, let's try and put a blade. I happen to have a blade and I hope I can find it now. I should be having a blade with me, yeah. And here it is. So this is a normal shaving blade. Normally this is made up of iron. Okay. And will you expect this to go to the bottom of the glass or it will float? Why will it float? Surface tension. But let's see if we can really do it. Let's see. It's very difficult experiment to perform because any small mistake on my part and the blade will go to the bottom of the glass. Let's see. Do you have a tissue? That's the best way to do it. Tissue. Okay, never mind. Let's just put it. Do you see blade is floating? Okay, can we focus on top? Or do we have a mirror? Do we have a mirror? Probably somebody will have a mirror, a small mirror. Is there a mirror with somebody is having a mirror? Yeah, I have a phone, but yeah, no. Let's just see. Is it on your phone? My phone is. Okay. So all right. So for the time being, can you bring the camera close? Is it possible? Can we show something on top? The top layer. Okay. Never mind. It's okay. So we'll come back to this. And because of surface tension, what we are seeing right now is a metal blade is actually floating on the water. Normally we'll expect it to immediately go to the bottom, right? So what is the origin of surface tension? Why is it that there is something called as a surface tension? Anybody who said surface tension? Yeah, go ahead. What is surface tension and what is the origin of surface tension?
Surface tension is the top layer of water which is not distracted.
But what is the origin? Where does it come from? Why is it that? So what I'm trying to say is, okay, so the question is very simple. If I do the same experiment in, let us say, some other fluid, let's say we take alcohol or some other material, let's say what else do we have? Fruit juice.
Fruit juice.
Let us say we do it in fruit juice. Will we see the same thing?
What about oil?
Oil, let's say oil.
I don't know, sir.
Okay, that's okay. Anybody else? The answer is correct. What is known as surface tension. Now what we are trying to ask is, what is the origin of surface tension? Why is it that there is something called as surface tension? And do we discuss surface tension in terms for liquids, or can we discuss it for solids as well? Okay, so just these are two small questions for you to ponder about. And now if I put a small soap on it, what will happen? Let's see. So right now the blade is floating and I take some washing powder. I think we have some washing powder here. No, this is not a washing powder. Washing powder is in the other column. Yeah, it's here. Yeah. So if I put some washing powder in it, what will happen? Let's say I take some washing powder. Did you see blade moving? You will not see it. Okay. What I suggest is this. When you go home, you do this little experiment. Take a small glass and add water to it drop by drop so that it doesn't overflow. And then put a blade. I can show you the blade now because it did not go down. I can recover it. So this is the blade. And once the blade is floating, you add some bit of washing powder in it. So what happens is, the origin of surface tension lies in the structure of water molecule and how different molecules interact with each other. So in that sense, water is a very strange liquid. It has abnormally high surface tension. So the water's surface tension is very high as compared to other normal fluids like oil or alcohol or juices. And that is the reason we see that things like blade can actually float on it. Where else do we see surface tension in nature? Have we seen insects walking on water? Right? So have you seen, you must have seen it in TV or during monsoon season in your surroundings as well, that wherever there is some stagnant water, you will find insects crawling on the water. Right? And do you see a slight dip near their feet? So if you observe the insect carefully, you will see that the water level, there is a slight curvature on the water surface. But the insect does not get immersed in water. It is able to walk on the water. Can we walk on the water? Can we walk? Can you walk on the water? Anybody? Can you walk on water, Shantanu?
No.
Any one of you? Have you tried walking on water? You have to walk on water. Okay, so that means like we walk on the soil. Can we walk? Can humans walk on the water? No? Why? Think about it. The insects can, but humans can't. You see the difference? So just think about it. And since you have thought about surface tension, and in the morning we did experiments on pressure and surface area and things like that. So that's the clue. And so now from surface tension, let us move on and let's look at something else. So what else shall we do right now is look at different temperatures. Okay, so let's take water in different cups. So let's say that this temperature is 20 Celsius. And I take one more glass of water and put water in this as well. Could you pass me some water? So what is the collective temperature of two glasses? This is 20 and this is 20. What is the collective temperature? What is the collective temperature? Anybody saying 40? Somebody says 40. Okay, why 40? See, the question is very simple. This is one glass of water. Let's say 20 Celsius. This is another glass of water, also at 20 Celsius. What is the collective temperature? Somebody is saying 40 and they have to tell me why 40. 20, okay, but 40, somebody is saying 40. 20 or 40? 20. Okay, but why 20? Normally you will not add. What is it? Okay. Now, let us say that, can we have some warm water? Or we'll have to heat some? Okay, let's heat some water. Let's heat some water. Where is our kettle? Yeah. Yeah. So, can I have a volunteer? One volunteer. Anyone? Yeah. Somebody. Somebody who has not, whoever didn't come up. Yeah, come. Yeah. This is lukewarm. That's okay. Okay. So you have to put 2 fingers in water and say whether you feel hot or cold. And if you switch, it's feeling warmer, right? Okay. So can we give her the mic? So what you did, so as a part of experiment, all that she did was, there was 2 glass of water, one with a normal room temperature water and a lukewarm water, and she put 2 different fingers, one from the left hand and one from the right hand, in each cup. Is that what you did?
Yes.
And then you were asked to swap it.
Yes.
Swap it, right? And then the question was, what the left hand felt was, did the left hand feel water warmer over the right hand?
Yes.
Yes. And your answer was yes. Why?
Don't know.
Okay, anybody? Yeah. So you can come up, do the experiment. Okay, all right, you can sit. We'll do this experiment with few more people, try to find the answer. Yeah. So you can give me the mic. So yes, put it more inside. Yeah. So which one is warm? Now just switch it. Now, are you feeling this colder and this warmer? So this is, now you are finding it more cold than earlier, and this one as more warm than earlier, right? And all that you did is you have changed the fingers. So why?
Because first we have put our finger in the warmer one. So our hand is adjusted to the warmer temperature. So when we put it to the colder one, it feels like plain.
Somewhat. Okay, all right. So let's go beyond this, and I would sit. Thank you. So when you go home, you take more such glasses at different temperatures and repeat the experiment and note down what you saw. Also, okay. So that's it. That's for the warm and water. And so now what next do you want to do?
Shall we do some experiments with candle?
Okay, shall we play with candles? Okay, candles, birthday candles. But do we have candles? Yes, we have candles. And here I have a candle. So Shantanu, tell me, what is so special about the candle?
I mean, if I light fire on the top, it will light for a long time.
Okay, but if I held a matchstick to the wax, will it start burning?
No.
Will the wax burn?
No, the wax will melt.
Is he right? But isn't it the wax that burns? When he's lighting the wick, isn't it the wax that burns? So the question is very simple. When the wick is lightened, so it starts burning and the wax also burns. But when he's holding the matchstick at the wax directly, the wax doesn't burn, it only melts and drops down.
Yeah.
Is that what you see? So why is it that the wax doesn't burn? So can we do this experiment? Can we just take a matchbox? We have a matchbox somewhere here. And just please give us a minute till we find our stuff. Okay. Yeah. So can we get a matchbox? Yeah. Okay. All right. So till we get the matchbox, let us look at few more balloon experiments. Okay. So let's take a straw. Where is the straw? Straw is here. And let's take two balloons. So all that I'm trying to do now is, let's take this straw, and I'm not able to separate it. Just, could you check the scissors? All right. Okay. And let's take balloons. Two balloons, no, the small ones. So let's blow up a balloon. Thank you. And we'll go back to the candles in some time. So let's take a couple of balloons. So I'm going to blow up the two balloons, inflate them. One somewhat this big, hold this, maintain it, okay? And one slightly bigger than that. Okay, so now they are very dissimilar, right? One is far bigger than the other, and now as a part of our experiment, we are going to join the two balloons with a straw and tie them. Okay, so what you have to do now, Shantanu, is, take the straw, put it in the balloon's mouth, and take this thread, and tie it. Tie it such that the air doesn't leak. Okay? Yeah, just take 2-3 turns, make it tight, just so that the air doesn't go out. No, take 2-3 turns, take 2-3 rounds first. No, just wait. Okay, all right. As long as we have two dissimilar things, it's okay. Just hold the balloon. And let's tie this so that the air doesn't leak. So we are only trying to stop air from going out, okay? But the pipe is open. Oops. Okay, never mind. So let's do some improvisation and let's tie it first. Okay. So in our tiny experiment, this is our tiny experiment. Okay. So have I tied it well? Looks like I have. Okay. Now you have to put that balloon in this and we have to tie it. Yeah. Put it in. Put it in. Yeah. Yeah. You can release it. You can release it. Release it. And tie the thread. Tie the thread is here. Thread is here. I think I lost it completely. Put it more inside. Put it inside. Guide it. Guide it. Guide it. More guide it. Now you tie it. Take 2-3 turns. Yeah. Yeah. Tight, tight. No, more. Air should not go out. Yeah. Yeah. Now tie one more knot. Put one more knot on top. On top is okay. No, one more knot. Yeah, that should be okay. Yeah. All right. All right. Okay. It's okay. All right. So now, thing is, what will happen when I open my fingers? The two balloons are of different size. Are they same size or different size? Okay. Now let's see if I open. Will you expect air from bigger balloon to go into the smaller balloon, or the smaller balloon air will go into the bigger balloon? Small to big. And why so? Let's see. Let's see. Indeed. Okay. So the question is why? The usual question, why? You saw the experiment, right? Or shall we repeat it? Okay, let's repeat it. What we do is we'll untie this. Yeah. Let's blow it up one more time. Okay. Yeah, tight. Tight on the straw. Huh? Put the knot. Put the knot. Put the knot. Put 2 knots on top. That's going to be good enough. No, it will leak. One will leak. All right. So let's see now. Right? So all the ones who answered that the smaller balloon will become smaller and the bigger will become bigger, can you explain why? What is the driving mechanism? Normally one will say that the balloon, the air from this balloon should go in this. Let's see if I can push it slightly, right? I am able to push it slightly. Slightly.
But not much.
Not much, right? So why is it like this? What is the reason?
The reason is that the smaller balloon will have less elasticity than the bigger balloon, so it will.
Not really, because balloons are identical. So the elasticity is same. And how do you define elasticity?
The smaller balloon will be less inflated, so it will be exerting more pressure. So.
No. So the pressure is basically what is the atmospheric pressure, which is actually both same on both the balloons. So think about it. Think about it. It's not a very trivial answer, but I hope you will be able to get it. So from balloon, let's go back to the candle because we got the thing. All right. So as a part of our next experiment, we are going to light few candles. And for lighting the candles, we have that base. Chalk fell down. Okay. All right, all right. So let's go back to the chalk and see, can we recover the chalks?
Sure.
Okay, wait. I'll get it. Okay. So this is the green chalk. Hold it. This is the orange and this is the red. Okay. Just show, are we seeing different colors? No. Hold it from the bottom. Hold it from the bottom. So are we seeing, when we look at this, yeah. Is it green and yellow? Do you see it? Okay, and
this one seems fully red.
This one seems fully red, and this is orange, but with slightly different shade.
Slight yellowish sort of.
A yellowish thing. So this experiment is all about what is called as chalk chromatography. What we saw was something called as a capillary action at work. So because of the capillary action, we see that the green color is actually breaking into two components. One is green and another one is yellow because the different colors were used to arrive at green and they are the ones. So where is this chromatography used?
It's in separating some chemicals or something?
Yes. So chromatography is used in separation of chemicals and it is one of the popular methods in chemical industry for separation of chemicals, or also identifying what chemicals are there. And now let's go back to our candles experiment. And to start with, can we have a beaker? Yeah, we can take this beaker. Could you please empty this? All right, we can put colored water in this.
You don't need this, no?
Not right now. We'll require it. So as a part of this experiment, I'm going to light candles and I'm going to take candles of same height. Okay. And light them up. This is one candle. This is my second candle. And can I have one more? This is my third candle. Okay. So I keep the candles in water and pour some water in this. So could you focus on this camera? And let's light the candles up. So this is another capillary action at work thing, and we'll come to how it works in a moment. Okay. Do you see all the three candles are lit? And now if I cover the candle with a container, what will happen? Let's see. And it has gone off in a moment. Okay. Now, why did it go off? Carbon dioxide. Okay. Now let's do one more experiment. And now what I'll do is I'll change the candles to candles of different height. Okay. So this is my tallest candle. And I take one more candle which is slightly shorter than this. Yeah, visibility could be a problem. But then we can always take one fresh candle and also take a bigger beaker. let's take a bigger beaker. Could you take out a beaker? There is a half-liter beaker inside.
6th children and 10th children, please go to planetary. 6 standards and 10 standards.
No, this one. Okay. So let's do this experiment again, and I have another beaker to cover it, and we will try to time as to which candle goes off earlier. Okay? Is this visible? Not exactly. Yeah. Okay. Now once I light the candle, it will be visible. Okay, so are we ready for the experiment? Okay, now let's see. I'll put this cover. So, did you see that there was a small difference between at the times in which the candles went off? Did you see that? So, which one went off first? And which one went off last? Shortest one. So, now why is it this way? Why did it not go other way around? Like, why did the bottommost candle did not go off earlier? So, what is the reason? Can we run the mic? Can we run the mic?
Because carbon dioxide moves up first. So the tallest candle goes off first because carbon dioxide moves up and
So,
not...
so if the carbon dioxide moves up, but isn't it heavier than oxygen? So should it not actually come to the bottom?
It comes down afterwards because it first goes up then comes down because of the heat of the carbon dioxide.
Yes, but from what you are saying, if the carbon dioxide is coming down, then the lowermost candle should go off earlier, right?
And the carbon dioxide exerted from the tallest candle touches the tallest candle and then it touches the shortest one.
But okay, any other answer? Let's look at any other response. Any other response? Yeah. Yes, go ahead. Sir, Bharat sir, she wants to say. Go ahead.
After the big candle will go, after small will go.
Yes, but your observation is correct. The question is why? Why is it not other way around? Why the smallest candle is not going off earlier and tallest one standing till the end? That is the question.
Don't know.
Okay, all right. Any other response? Any other response? Did we see this experiment or shall we repeat it? Do you want to repeat the experiment? Okay, go ahead, say it.
I want to tell the answer, sir.
Go ahead.
The answer is that oxygen was more at the bottom.
From where?
Near the shortest candle.
But why? Why is it like this? That's the question. See, the thing is, now I take this container. Can we say that oxygen is more or less somewhere? Can we say that?
Right now it is, cannot say, sir.
See, right now it is having air.
Yes,
right? And we can say that it's uniform. So whatever oxygen is there at the top will be at the bottom as well.
Yes,
right? So when you say that there was more oxygen available at the bottom, my question is why?
because the longest and mid-range candle were at the top right, sir. So it absorbed more oxygen on the top.
Well, not really. And basically, see, our initial hypothesis was, if I take only one candle, let us say that I take only one candle, I repeat this experiment. Can I have one more paper plate? Yes. Okay. See, let's repeat this experiment. Now I take the taller candle. Place it in this and put some water. Why is it that nobody is questioning me why I am putting water at the bottom? Is it necessary? Why is it necessary? No. Okay, let's time it now. Let's say for how many seconds does it last? Around 11 seconds? Okay, and when you were looking at the flame, initially the flame was slightly fat, right? Did we see it growing taller? Let's now look at the shape of the flame. Okay, just look at the shape of the flame and see if it changes with time. Is the shape of the flame changing with time?
Yes.
Did it?
Yes.
Okay. So the usual question as to why. So one is time, and the second question is why did the shape of the flame change? Thirdly, if we have to say that the oxygen is consumed, can we say that the entire oxygen is consumed?
During combustion, oxygen is used. Okay. While the flame is growing brighter, more oxygen was used. But the dispersed carbon dioxide is lighter and it is hotter, so it rises up, and there is no oxygen present above because carbon dioxide has taken its place. So the oxygen is there, it is present, but it came down.
Okay, so now I will give you a little homework. Can I give you a homework? Okay. So you have to find out chemically what is wax. This is wax, right? What is the chemical formula of wax? Secondly, if suppose you have burnt 1 gram of wax, how much is the energy produced?
In joules.
You can find it in calories, any unit you like. And third question is, how much oxygen is still left in the beaker after the candle goes off? Okay, so they are the 3 things. That's your homework. Okay, and that's a homework for everybody. You are in the 11th class. 10th class. So you should be able to do it. So now, see, why is it that I am showing a candle? Why is it that most of the physics demonstrators will go to candle? Because this is a very fundamental entity in a way, because it is having hydrocarbon. Wax is a hydrocarbon. So for any burning or combustion action to happen, you need 3 components. One is hydrocarbon that can burn. Second is oxygen that can think. And what is the third component? Heat, temperature. Yeah. So we must have all 3 components. There has to be an adequate temperature, there has to be a hydrocarbon, and there has to be a supply of oxygen. Okay, to sustain the combustion. Now, why is it that combustion we show? Because it is one of the important processes in life, and it involves 2-3 fundamental things. Like when we blow the candle, okay, why does the candle glow off? Suppose I lit the candle and I blow it off. What exactly is the mechanism which turns it off? So, am I depriving it of oxygen, or am I reducing the temperature? Reducing the temperature that kills the combustion, or am I cutting off the wax supply? So think about it. These are the three questions that I want to pass to you. And now, Shantanu, what next?
Since we did candles, shall we do some optical experiments
Like?
Light.
Light, but what light? Okay, let's take a beaker full of water. Shall we do arrow reversal?
Okay.
Arrow reversal, okay. Now, yeah, take a mug full of water, and let's take a, yeah. No, I'll require a pen.
It's in my pouch.
Yeah, got it. And a paper. Yeah, okay. Yeah. So, let us say that we are having an arrow which is pointing like this. So let's make some space and take the bigger beaker. Let's take the bigger beaker. Bigger. The other bigger. Yeah. Okay. Now, do you see this arrow? Do you guys see the arrow? Is it? Okay. And now let's pour some water in it. Let us see what happens to the arrow. Take some more water. Take some more water. Pour in it. Do you see the direction of the arrow reversed? See, it is this. Right now it is this. I bring it down. And do you see it reversed? Do you see it? Let's do it one more time. This is the arrow which is towards Shantanu. Okay, I'm only pushing it down and it starts pointing towards me. Do you see this? Okay, so again the usual question. Exactly. Why? What causes direction to reverse? Is it really reversed? But when we see it, it appears to have reversed. Right? Why does it reverse? Anybody in the back? People in the back? Yeah, go ahead. Yeah.
The answer is refraction.
Okay, if I put my finger in it, do you see it swollen? My finger is usually this thin or this thick. Do you see it swollen?
Yes.
Okay. Now let's put a pencil in it. we had a pencil or a pen. Let's put something in it. Yeah. Or pen. Let's see what happens to the pen. Do you see pen bent? Do you see a pen bent or it's straight? Hello, hello. So this is refraction. Okay, and what else? Make a guess, make a guess. Make a guess. If you don't make a guess, then I'll take this as a homework. Okay, take it as a homework then. All right, so what next?
Sir.
Yeah.
Sir, can I say the answer? Sir, can I say?
Yeah, go ahead.
Sir, because of the light rays which passes through the glass.
So what happens?
Sir, the light rays reflect because of the water and the arrow turns.
Not really. Think again. Yeah. Okay, so no, we'll ask them to do it in their place. You will conduct this? So, all right. So, let's do one more experiment. And this experiment, every one of you is going to do. So, if you are having bags in your lap or anything in your hand, just keep it down. Make your hands free. And do what Shantanu does and what he says. Okay? So, this is a very simple experiment. You don't have to put anything in your eyes or ears. Okay?
So you just have to take your 2 index fingers.
Yeah. So, I'll hold the mic.
Okay, 2 index fingers. Now you can try to just touch them like this. They'll touch, right? Okay. Now we'll do the same thing, but we'll keep one eye closed and we'll try to do the same thing.
Slow. There is no hurry.
Are you able to do it?
How many people missed?
Everyone is able to do it?
No, they missed. All right, and let's take one more part of this experiment. So let's close the other eye. See, thing is, both eyes open. You have to just take the fingers close and make them touch each other. Next is, again take it away. Close one eye and try to bring the fingers close. And you make sure that they are coming together in front of your nose. And I missed. See, they have to touch tip to tip. It's something like this. Okay, hold your arm straight. Hello. Listen. Just see how the experiment is to be done. Your arms have to be straight. Okay, bend your elbows. This is the position. Is this correct?
Yes.
Yeah, and take it away. Okay?
Yes.
And now close one eye and very gradually try to bring them close so that fingertips touch each other. And I missed. How many missed? Yeah, now many people have missed. Now let's close the other eye and do the experiment. And let's see how many people are able to touch the fingers. You were able to touch, okay. All right. No, you missed. All right. How many have missed? You have to be honest, because missing is actually correct. That's the way human functions.
Yeah, I mean, if you can't see, how will you?
See, the thing is, again, it's very simple. See it again. Okay. Stretch your arms, keep your fingers pointing outwards, and then close one eye and slowly bring your fingers together. Bring them together. You have to be slow. Keep the closed eye closed, and then try to touch the tips. See, the fingertips have to touch each other like this, not sideways. Fingertips have to touch. Are you able to get it? Hey, don't do that. Let her do it. Let her do it on her own. Okay, now change the eye. Now the eye that you had kept open, keep closed, make it closed, and open the other eye, and repeat the experiment and see what happens. So, and also you have to tell them why is it like this. Let them do the experiment. Just ask them if they are ready for the answer.
So can anyone explain why some of us have missed it? Why some of us couldn't correctly touch when we had one eye closed?
Because for humans, two eyes are required for telling the appropriate distance for.
Correct, but why is one eye not enough?
Because there are two eyes which.
In one eye, why can't I see the distance?
One eye, it is like a screen. It cannot tell the exact depth for it.
Correct, one eye is just a screen, right? You cannot actually see, but with two eyes, you are able to make the distance, depth perception. Is that right, Ullas? You need two eyes for depth perception?
Okay, all right. So now let's do one more experiment. All of you, listen. Just one more small experiment. Are you ready for it? Okay. So what you have to do is, you have to hold your palm in front of your mouth and open your mouth wide and blow. Just do it. I mean, did you experience a hot air or did you experience a cool air? Has everybody done it? Not everybody has done it. I say it again. Hold your palm in front of your mouth, open the mouth wide and blow. Do it. So, did you experience a warm air or was it a cold air? Okay, now the same experiment, but instead of opening the mouth wide open, you keep it only slightly open and blow. And now say, was it cold or was it hot? Did everybody find it cold? Okay, now are we ready for the usual question?
Why?
Exactly, why? It's the same thing, right? Air coming out of your own body, your body temperature has not changed. Your hand temperature has not changed. The distance has not changed, but once you blow out widely and once you blow out coolly, and you see a different effect. Why so? This is a very simple question, very simple experiment, and you can do it yourself. Think about it, and we'll come back to it. Or shall we take it and now, right now? Anybody wants to offer? Yeah, go ahead.
Sir, because when we open our mouth wide, there is less contact of saliva which cools the air.
And in the other experiment?
When we close our mouth, in the surrounding of our mouth, there is saliva which cools the air. So,
How will the saliva cool the air? Because saliva is inside the mouth.
so when we blow, it
See,
comes in.
the temperature of saliva is same as temperature of your mouth. It's not at a different temperature. So the thing is, yeah. Here.
First time, while we blowing, air was come from our inside our body. In second time, while we blowing, the air was coming. While we take the air from nose and directly that come from our mouth. That doesn't go to the inside chest or other organs. So it is cool.
Are you convinced yourself? Are you yourself convinced with the answer? No. Okay. All right. Any other solution? Yeah, one in the back. No, that's not the thing. We'll tell you the reason. We'll tell you the answer.
When we blow the air through narrow passage, the pressure will be high, so the compressed air will be colder.
Compressed air will be colder.
Yeah.
But why should the compressed air become cold?
Due to the low kinetic energy between the air particles.
No. Think again. Anybody else? Okay, we'll come back to this question. And let's look at something else. And what is it that we should be doing now is... Diffraction will not be able to show here.
Sir,
Yeah. Okay.
Sir.
Yeah.
When we open our mouth and exhale,
Yes.
the body temperature, the excess heat will be released together. But when we keep our mouth in this position, when we blow, the wind speed will be more, and it will become cooler.
But you have a control, right? If you gradually do it, will you see something different? You'll still see the same thing, right?
Yes.
Think again. And meanwhile, let's do one more surface tension experiment till our friend Shantanu finds out another bright experiment, or we'll take a puzzle. Shall we take a puzzle? No, we'll take a puzzle. Shall we take a puzzle? Okay, let's take a puzzle. So the two puzzles that you had designed for them, specially for them.
Yeah.
Okay, so you wear this for some time.
This mic will work better.
Girls of 8th, you won't get planetarium if you make so much of noise.
Okay, I need two people to come and play a game. Anyone? Maybe one boy and one girl. You want to come? Connection loose, and okay. Only two people. Okay, you both. So you can just watch us play the game. Okay. So it's a two-player game. The rules are simple. What you do is, so there are two players, player A and player B. So who wants to play the game? You want to play? Okay. ನಿನ್ನ ಹೆಸರಂತ Gahan. ಮತ್ತೆ? Okay. Gahan and Arush will play this game. So what they will do is they'll alternate. First Gahan will play, then Arush will play. So Gahan, you can play first. So the point is, we'll start at the bottom left corner of the grid, and the target is to reach the top right corner. Okay. And the move you can make is, you can go how many steps you want up or how many steps you want right. So you play with me once, I'll explain. So you can play. So you're the first move. You can try to play the first move. So you can go how many steps, ಎಷ್ಟು steps ಕೂಡ ಮೇಲೆ ಹೋಗ್ಬೋದು ಅಥವಾ ರೈಟಿಗೆ ಹೋಗ್ಬೋದು. So illinda you are here, player A. You can go how many steps you want up, how many steps you want right. Goal is next ನಾನು ಆಡ್ತೇನೆ, then you will play, then I'll play. The goal is we want to reach this. The first player to reach this point is a winner. Okay. ಈಗ ನೀನು you can go how many you want up or how many you want right. ಅಲ್ಲಿ ಹೋದ್ರೆ you go there, then I am the second player, I can immediately go here. So I win. Okay. So we'll play one more game. You can start. So you can start again. Okay. So I'll go here. So we are alternating turns. This is Gagan's turn. Now it's my turn. Now it's your turn. Why don't you go up? Up ಯಾಕೆ ಹೋಗೋದಿಲ್ಲ? ನಾನು ವಿನ್ ಆಗ್ತೇನಾ? ಓಕೆ. ಹಾಗಾದರೆ ನಾನು ಇಲ್ಲಿ ಬರ್ತೇನೆ. Oh, I'm trapped. So Gagan wins this round. Okay. Okay. You both can play now. Gagan ಮತ್ತೆ ನಿನ್ನ ಹೆಸರು? Gahan. ಆರುಷ್. ಗಗನ್ ಮತ್ತೆ ಆರುಷ್ ಆಡ್ತಾರೆ ಈಗ. Unfortunately. Okay. You want to play? Play. Maybe can any girl volunteer come to join to play? A new game. Okay. Hardly. He has not played. You can go here. So he's first player, you're second player. Okay.
Can I click this?
Thinking. Oh, but then they'll win. Oh, close. Nice. Okay. Okay, maybe I'll have one more volunteer. One. One. Yeah. Yeah, maybe I'll just take 2 more minutes. Yeah. But they'll not have phones, no? I'll give it. Okay. So now what I'll claim is, what is your name?
Abhishek.
So, no, that is, I think that's this problem. Okay. So Abhishek and I will play now. So Abhishek will play first and I'll play second. And I will claim that I will win this game. Whatever moves Abhishek makes, regardless of that, I will always win the game. So let's see. You can play now. This one. Okay, so I won the game. So my claim is whatever move Abhishek is making, I can always win. So does anyone see the strategy I'm using? Like, why am I always able to win? So maybe you can. It's your game. Maybe you can play now. What's your name? Advit. So Advit will now play first, and again I'll always win. No. Okay, so I won again. So, does anyone see why I am able to always win? Like, what strategy I am using to win?
Any guess as to how he is managing to win all the time?
He's copying me.
Yeah, go ahead.
I am copying, but how?
Thank you, volunteers.
Yeah, you can say if you want. Okay.
So now, okay, we'll take the answer. Somebody was raised his hand, right? Wow. Go ahead. Why did he manage to win all the time? Could you come in front? Come in front, please. Please come in front to say that. Yeah. Please come in front. Because the mic man is tired. He has been running all through the day. Yeah. You can stay there. Yeah. Go ahead.
Because he went in the diagonal.
Correct. So
Correct.
I went in the diagonal. So,
See, they are catching your tricks.
So I'll play a new game. This time I'll highlight the diagonal. So right now all the diagonal entries are highlighted. So what I do is I do some simple trick. So whatever move my first player plays, I'll simply go to the diagonal. So here's the first player. Second player will simply go to the diagonal. So whatever move the first player is making, I'll just copy and go to the diagonal. In this strategy, I'll always win. Does that make sense to everyone? This is just a simple game theory trick. So we observe there is a winning pattern, and once we observe winning pattern, then the first player has no chance. The second player will always win.
Okay, so now let's go back to our water game, and now I claim that I have water in this syringe and I can make it boil.
No.
How? Just pull it like this. Okay, all right. Let's see this. Let's see if I'm able to boil it. Can you focus the camera on this? Yeah, let's see this.
The students, those who have come from outside, hope you have watched Planetarium.
Do you see it bubbling?
Those who did not, please come and join now.
Is it boiling?
Those who did not watch Planetarium.
So, did you see bubbles coming out? So what was it? Let's repeat it. Do you still see it? Is it hot or cold? Can anybody come and touch and tell me? Is it hot or cold? Somewhat hot. But is it hot enough? Not really, right? Let's repeat this. See, all that I am doing is I am removing all the air from the syringe. Okay? Closing the syringe and pulling the piston. Right? So what we are seeing initially is this. We all know that air dissolves in water. Do you believe this? Air dissolves in water. Okay. So what we started with was a lukewarm water. We had boiled the water, so all the dissolved air had gone out. We took that water and now we are reducing the surface pressure. We have seen the vapor pressure phase diagram of water, right? Pressure temperature phase diagram. So at ambient pressure, water will boil at 100 degrees Celsius. But if I reduce the pressure, then the boiling point will also come down, right? So if we go to higher altitude regions in the country like Ladakh, which are like about 11,000 feet above sea level, we'll see that the pressure there is very low. So water effectively boils at a much lower temperature. So food cooking will take longer. Though we'll see that, okay, water is boiling, so my rice should be cooked, but it will not get cooked. So that is why we'll always use what we use at homes? Pressure cooker. Because in a pressure cooker, we can look for a constant pressure for the thing to work. So this is our tiny experiment to demonstrate that by reducing the surface pressure, we can make the water boil at temperatures below its normal boiling point. But mind you, even though it is boiling, will it be hot? It will not be hot because its boiling temperature has come down. Okay, so this is one tiny experiment of boiling. And now let's see if we can build some motors. We all have seen motors, right? So now what I have is a battery, the small battery, and I have a magnet, and I have made a copper coil. So a few turns of copper coil. And now let us see if when I insert it into the circuit, if it starts rotating. Could you focus on this? Let's see this.
So there's a battery and a magnet.
Yeah, a battery and a magnet, that's all. Do you see it unstable? Now I just need to give it a small kick. Let's make it first horizontal, stable. Yeah.
Oh, it's rotating.
Do you see it rotating? Is the motor running? So can you guys build such a motor at home? Will you do it? All right, so make it and send us the photos. We'll be very happy to receive the photos. So this is one small motor demonstration. Similarly, let's see if we can have some other motor pattern. Hey, where is our magnet pendulum?
It is here.
That, okay. All right.
Oh, it is stuck.
Oh, it is, okay, because it's very strong. All right. So let's see. Now this is another motor demonstration. So we take this screw, we keep it slightly here, and now I need a piece of wire.
Oh, will it rotate when you connect?
Let's see, let's see. Will it rotate? What do you guys think? Will something rotate? No, it's not. Slightly. Maybe we should make the conducting path accessible. Let's remove the tape. Yeah. So thing is, so this is our part is ready, and let's see now. Let's connect this electrode.
Oh, it's rotating.
Is it rotating? Is the motor running? So this is a small demonstration of what is called as a homopolar motor. That is, it's a single pole motor, and okay, all that I am doing is I am just touching the wire to the magnet and keeping it centered, and let's run it. Okay? So will you guys try to build such things at your home? Okay, do build it. Keep wondering about why the things are the way they are. And now, before we end, shall we do one more round of liquid nitrogen, especially the people who came now? Have you seen liquid nitrogen demonstrations? No. The people who came now. Have you seen liquid nitrogen demonstrations? Okay. All right. So we'll take this as the last demonstration. And for that, let's take some liquid nitrogen. So, all right. There was one more box, no? Yeah, we'll take this box. This is bigger and better. Hold the other side. Yeah. I think this should be okay. Yeah. Okay, so let's take this nitrogen. Here. Now I want 2 volunteers to come on stage. Can 2 volunteers? Two, only two. Okay, I'll give you a piece of paper. You have to fold it the way I show you. Okay, come. You can also take one. No, take this. Take this. And now you have to, okay, face the people. Just fold the paper like this. Come in a line. Please come in front. Please come in the front. Come in, stand in the line. Fold the paper like this. Do it like this. Make it sharp. Yeah. All right. Put one more fold. No, like this. Okay. And open it slightly from one side. Like this. Okay. Open it. Yeah. Open it. Keep it open. Yeah. And hold it from the top. Hold it here. 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 No. Okay. Okay. And I'm going to pour nitrogen in this. No. You have to hold it like this. Hold it like this. Don't touch at the bottom. Hold it only at the top. Hold it only at the top. No, don't touch at the bottom. You can hold it here if you want. One hand here, one hand here. Okay. All right. And now I'm going to put nitrogen in it. Let's see what happens. No, you stand there. You be where you are. I'll come to you. Okay. All right. Are you scared? No, you're not scared. Okay. Let's see. Okay. Is nitrogen leaking?
Oh, something is going below the paper.
Is the nitrogen leaking? Is it nitrogen or is it something else? Are you seeing it? But is it leaking? No? 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 Okay. So if you think it is leaking, it must have a hole. Right? Okay. Now let's just wait. Give it to me. Give it to me. Let's discard all the nitrogen. And you show it to people. Is your paper wet? Is the paper wet?
Wait.
Is there a hole? Hold it to the light. Is there no, you have to see. They will not be able to see the hole. Is there any hole in the paper? No, you see at the light. You keep it like this. Hold it against the light. If there is a hole here, you should be able to see bright light. Do you see it? Do you see it? Do you see it? So is there a hole in the paper? So there is no hole in the paper, and allow me to do it again. I'll do it this time, just to make sure that they didn't cheat, which I know you didn't. Okay? So let me just pour some nitrogen in this. So what is it that is flowing down? If it were water, we will find that the paper will become wet. But in this case, was the paper wet? Paper is dry, right? So now, Shantanu, could you take a matchstick or a candle? Please light a candle. Light a candle. Hold it horizontally. Yeah. And try to bring it close to the flow. Yeah. So what is happening? If it were water, will the flame go out because of water? Okay, so now this time it went off. So what is happening is, can you burn it, light it one more time? You guys can sit. Thank you. Okay. All right. Now. Okay. So what is happening right now is, because of the cold liquid nitrogen inside the paper, there is a condensation of nitrogen gas in the air, and it is liquefying and flowing it down. But mind you, it cannot wet the paper, and this brings me to another point, as to give you a small homework as to what do we mean that a paper is wet. If we put some water on it, like I put some water on the paper, it will get wet, right? It will get wet. If I hold it against the light, I can distinguish between the wet region and the dry region. Do you see this? So when you go home, do this little experiment, put a drop of water on a piece of paper and see it against the light, and you will be able to distinguish between the wet region and the dry region. But the liquid nitrogen is not wetting the paper. It is not at all wetting the paper. So think about it, why water is able to wet the paper, but liquid nitrogen, which is also a fluid, that does not wet the paper. So think about it, what is this process of wetting, and why does nitrogen not wet the paper but water does? So that's another piece of homework for you. And we'll end with the demonstration of superconducting levitation. So we all know that we take this small torch. So the ones who were here in the morning, they have of course seen this demonstration, but to them it will be a repeat. But just look at this torch and look at the brightness of this lamp. Could you focus on the lamp, please? Okay, and just take some nitrogen. Take nitrogen in the mug. Okay, and I'm going to dip this copper coil in nitrogen, and let us see if the lamp brightness changes, if it becomes brighter or less bright. What do you see? Take some more nitrogen. More nitrogen. Wait. I'll do it. Yeah. But take it full. Fill it completely. Yeah. Let's immerse it fully. Yeah. So do you see that the lamp is glowing brighter? Okay. And now as I take out the copper coil, it will slowly lose the brightness and it will become progressively less bright. It will take time because copper will not warm up instantaneously.
It will become slightly.
Yeah, it will. If we want to accelerate it, we'll have to put it in warm water. We can hold the thing in water. And it is losing the brightness.
Yeah, it's dimmed.
Right? So now this brings to another phenomena called superconductivity. And to demonstrate the superconductivity, we have a magnet. Where did we keep that set up? I think I kept it here. Give me a moment till I find it. Yes, this. Could be. Yeah. So I have a tiny setup. And let us see floating. Superconducting levitation. So to all the people who came in now, what we do at our place called Tata Institute of Fundamental Research in Mumbai is it's a science research institute which is involved in doing fundamental research in physics, chemistry and mathematics, biology and computer science. So how many of you think that whatever knowledge was to be gained by mankind is already discovered? How many think that? How many of you think that whatever knowledge, scientific knowledge is to be gained, is already found? Nobody. So that means you think everything is known. Okay. So the thing is, mankind has a lot of questions in fundamental sciences that are not yet answered, and our institute is engaged into some such pursuits. And if you want to become a scientist, that is one place to look forward to join for your research activities. And so now let's see if our superconductor is ready to float. Do you see it floating? Could you focus on this? Okay, let's do it one more time. Keep it focused on this. We'll repeat it.
It is floating.
Okay. One more time, because I understand that it's not very visible.
You can maybe move this.
Thing is, what if we keep the magnet on top of this? Is the magnet floating? Yeah. We'll stop. Pour some nitrogen. The best way is to okay, and as it slowly warms up and loses superconductivity, it is going to drop down. All right, so this is about superconductivity. So we'll keep doing this and take questions. So if you guys have questions, please go ahead and ask. So Mike, volunteer, you are ready. Yeah, please come in front. No? Please come in front to ask questions and take the mic from him.
Sir, the experiment you did now, what is below the magnet?
Below the magnet, this is just an aluminium piece. We have pasted the magnet on it for support.
Okay, sir.
That's all. Yeah.
What if we cool the magnet?
Its magnetic intensity will go up, that's all. So the thing is this. Oh, we lost it. Okay. Just skip focus. See, this is one of the phenomena that mankind has not yet understood. We know it happens, but we don't really know why it happens. So this is still a subject matter of research as to why there is superconductivity in certain materials, and in certain materials it is not. So this is one of the open questions to think about. So yeah. All right, so you guys have questions to Shantanu, please ask. And to the people who came now, Shantanu is from Udupi. He speaks Kannada as well as Tulu. So if you want to ask in Kannada and Tulu, you are welcome to ask. So please go ahead.
Yeah. Sir, just now you played in laptop some game, right?
Yes.
What is the name of that game?
I just call it grid game. I don't think there is any particular name to it. Yeah.
So, is it there on your website, the games?
It is there on my website, which I will maybe share with the organizers.
Okay. So, he has his personal website. He develops such games as his hobby. And some games are there on his website for anybody to play.
Yeah.
So, he will give it to your teachers. Yeah. So, all right. So, with this, we wish to thank, both of us wish to thank all of you for your patient listening to us, and thank the Vivekanand Foundation and committee and teachers for inviting us to this place. So, thank you very much. Be curious, keep playing, and work hard. That's going to be our message. Thank you.
Thank you, everyone.
Thank you.
Over the past 2 years, we have gathered here at the valedictory function of Day 2 𝐷𝐴𝐕𝐲 2025. And on this occasion, I'd like to welcome all the dignitaries on the dais and each one of you who are present here. And we directly move on to the session of prize winners. And may I invite Srimati Hema Bhatt to announce the prize winners.
Jai Shri Ram. I am delighted to announce the prize winners of today's inter-school competition for grade 6 to 8. I respectfully request our guest of honor, 𝐒𝐻𝐵 sir and Shantanu sir to kindly give away prizes to all the winners. I request all the winners to please come forward as their names are announced and receive their prizes. First place in the science quiz goes to Sri Krishna B and Sinchana P from Vivekananda Kannada Medium School. Second place goes to Sharanya GA and Aditi Bhatt from Manipal School. Let us clap for all the participants for their great efforts. Third place goes to Pratiksha Deepti U and Sharati Chanila from Vivekananda English Medium School. Next, we have the result of working model competition. First place goes to Anaga P and Aradhya from Vivekananda English Medium School. Second place goes to Aditya Achar and Akash J. Moili from Dr. M. Ramana Shetty Memorial English Medium School. Third place goes to Abhinav PN, Vivekananda Kannada Medium School. Next, identification of plants. First place goes to Dhriti Prabhu and YJ Danish Gowda from Vivekananda English Medium School. Second place goes to Garima B and Shreyash AJ from Vivekananda Kannada Medium School. Third place goes to Prapti K and Pranati B from Priyadarshini English Medium School. Now I would like to announce the result of the poster making. First place goes to Likita and Atmika from Vivekananda Kannada Medium School. Second place goes to Akshara and Advita from Bala Vikasa English Medium School. Third place goes to Sanvi Sharma and Adviti Ajila from Vidyagiri School. Now we move on to the prize winners from the grade 9 to 10. Here are the results for reels making. First place goes to Vanil Vishwakarma and Aditya Acharya from Vivekananda Kannada Medium School. Second place goes to Pramad Shanbog and Ganashyama from Vivekananda English Medium School. Third place goes to Aisha Dania and Mohammad Naushik, Bala Vikasa English Medium School. Wait. Next, meme creation. First place goes to 𝐴𝐴𝐽𝐻𝐿 and Bhuvan from Vivekananda English Medium School. Second place goes to Achintya Krishna and T. Pratham Rao from Vivekananda Central School. Third place goes to Abhay and Suvidha from Manipal School. Third, sir. Next, we move on to the result of Eco Champions. First place goes to Chandan and Shubhan from Vivekananda English Medium School. Second place goes to Rishona Sansia Pinto and Ananya M from BRMPC Public School. Third place goes to Manvit Shankar and Tanish M Bhatt from Vivekananda Central School. Extempore speech. First place goes to Atit H. Rai from Vivekananda English Medium School. Second place goes to Danyashri HP from Vivekananda Central School. Third place goes to Kanishka Manoj Karkera from NITK English Medium School. Now, we are proud to announce the result of overall championship. Overall runner-up award goes to Vivekananda Kannada Medium School by securing 120 points. I request teachers and students to join and take the award. Next, the overall championship award goes to Vivekananda English Medium School by securing 180 points. I request teachers and students to come forward. Congratulations once again to all the winners and participants for their hard work and dedication. Thank you one and all.
I request any student or teacher to share the feedback.
Good evening everyone. I am Kanishka from NITK English Medium School. All powers lies within you. You can do anything and everything. With the sacred words of Swami Vivekananda, we sincerely thank Vivekananda Central School for organizing Avishkar, a wonderful inter-school competition. Thank you for providing us the meaningful platform where we could showcase our talent very confidently and with a great courage. The entire arrangement was excellent and all the teachers were extremely friendly and supportive, making the day one of the most memorable one. Thank you.
Good evening everyone. Myself Lavanya from Sri Ramakrishna High School. Respected guests, I enjoyed so much today. Me and my friends had very good day and the planetarium was so good and we had good experience inside that. And also the experiments, we had more than like 20 to 30 experiments today. It was not just a workshop, entire syllabus of science. We had so fun and the day went so fast. So we are sad to go home again. So thank you for the Vivekananda CBSE for organizing this much good program. So yeah, thank you everyone.
Jai Shri Ram. Good evening. Myself Gautam Krishna. I am from Vivekananda English Medium School. So since morning it was very good. The food was amazing and the planetarium, I can't express in its words. So the competitions also went smooth and the workshop, it was amazing. So I felt happy and learned many things. So I would like to thank everyone for this opportunity and also us CBSE to organize many more events like this. Thank you.
With deep gratitude and utmost respect, we would like to honor Shri 𝐿𝐴𝐵, Scientific Officer, TIFR Mumbai, and Shri Shantanu Esrai, Research Scholar, Mangalore, who conducted an inspiring and insightful session for our students. May I request Shri Bharat Pai, the correspondent of our institution, to present a memento as a token of gratitude.
Students, today's wonderful session wouldn't have been possible if not our volunteers were not there. So big round of applause to our volunteers and the teachers who made it possible. We are truly proud of you. A big salute to the Scouts and Guides team, our students from grade 6 and above who volunteered today. Your selfless task truly inspired us. Thank you one and all. And before that, we conclude this formal vote of thanks by Madam. So please, Madam.
As we come to an end of this memorable day, we express our deepest gratitude, our guest of honors, and all the dignitaries on the dais, and a heartfelt thanks to all the participants and accompanying teachers, and special thanks to the parents and the invited guests, press and media members for covering the event. And as Sir said, a special mention to all the teaching and non-teaching staff, and heartfelt appreciation to all the volunteers. Thank you very much. And all are requested to be seated for Shanti Mantra.
ಸುದ್ದಿ ಚಾನಲ್ ಕ್ಷಣ ಕ್ಷಣದ ಸುದ್ದಿಗಾಗಿ